I'm Josh Dennison, cover Northern Ohio, Western PA. Dave and I were kind of tasked with this to come up with this minimum technical competency. There's a lot of people, even in this room, that refer to me as the pneumatic expert. That's not true, so don't believe that. Not a pneumatic expert. I'm still learning. Dave knows much more than I do, but this is the basics, okay? I know the basics very well. There's things that I get stumbled up on every day, so don't feel like any question is too dumb or small. Ask questions. My number one goal, and I'm passionate about this, is teaching you guys the basics. When it gets to some more advanced stuff, I can cover some of that stuff, but usually I'm going to hand that stuff over to Dave, okay? So the basics are very, very easy to understand. This, however, may be daunting, to say the least. Does anybody know how to read this schematic from start to finish? So there's nothing complicated here at all, but a lot of people don't understand this. So that's what this training's about. Now, at the end of this training, you should be able to pick parts of this out and decipher what's happening, okay? So starting down here, we've got a shut-off valve here. This little arrow here is your incoming pressure. We've got some FRL here. We'll talk about what FRL is. We've got some mufflers. We've got a valve manifold. We've got some grippers. We've got some cylinders. We've got some vacuum stuff going over here. So we've got a lot of stuff going on in that schematic, and it's on your handout. So as we go through this, try to pick out what is what when we start talking about FRLs. Try to figure out where the FRL is and what it looks like, and we're going to look at symbols. Dave's very passionate about teaching the ISO symbols for all the valves and cylinders and things like that. There's a lot of valuable information there, okay? So I'd like to start with this. It gets everybody's attention. Everybody starts to freak out a little bit. Oh my God, I don't know if I'm going to be able to understand this. But trust me, by the end of this training, you should understand this or be able to decipher this piece by piece. You may not be able to burn right through it, but you should be able to tell piece by piece what everything does, or at least have a very good idea. And if you don't, I'm blaming you for it, okay? Ask questions. Make sure you understand this stuff before we end today and move on.
This slide's very important because a lot of the times we'll go into a customer and be like, they have a problem, right? Troubleshooting should be your number one way to gain a customer, right? It is the easiest way to gain a customer. You walk into a place and like, hey dude, my rotary's not working. And you look at this schematic, you're like, I don't know where the rotary's at. So, you know, there's a rotary actuator up top here, right? Okay, what's wrong with that? Go back through and troubleshoot it. We get it. This is how Josh and I gain these customers and why they want to talk to us directly, because we help them out. If you guys could help them out, boom, they're going to call you every time. They have an issue, they have a new project, anything. They're like, hey, Nick helped me out on that last one, man. I'm going to give him a quick call. So this is very, very important, you know, in our jobs.
And a lot of times we get customers that, I know at least you Ohio guys, has happened a lot recently. You know, we'll walk into the customer and they say, hey, here's what we're trying to do. Can you give me valves for this, cylinders for this, and whatever? And we're going, we don't know what you're really trying to do. Well, wait a minute, I have a schematic. So they hand you the schematic, and some of the sales guys just kind of, you know, glaze over. They don't know what they're really looking at there. And so I'll take a good 5 minutes and try to decipher what they're doing. There's not a lot of information here, so if they said, hey, I need cylinders for this project, and they hand me this, there's not enough information here to tell me, you know, you're going to need this cylinder, this bore, this stroke, you know, all these features and all these things that go with it. It'll tell me what kind of valves, but it doesn't tell me what size of valves, things like that. But this gives me an idea of what they're doing, so I can start asking questions, okay? All right. So as Dave said, minimum technical competency. We're doing this today is just pneumatics. You've got this for several different areas. So we've got a big benefit here that we broke this out, and this isn't a 5-day training. This is a 1-day course here. Basic pneumatics. You've got, you know, the other sections they're going to break this out into. So you don't have to focus on more than just pneumatics, okay? So don't panic. This will be easy for you guys. We're going to start very, very basic. So what are pneumatics? Well, everything on your screen can be considered pneumatics, okay? So we've got cylinders. You guys have probably all seen cylinders. Some of the new guys, I hope, have seen cylinders so far. But we've got cylinders, we've got grippers and slides and vacuum products and things like that. You guys have probably all seen these on the back of semi-trailers. Those are those airbags, those Firestone airbags. Those are pneumatics, okay? And there are valves. Nick knows that more than anybody working in transportation. Blowing up a balloon for your kids, it's compressed air. That's what you're doing. You're adding compressed air, and that's pneumatics, okay? So there's nothing real complicated here. How do we compress air? Well, we call that an air compressor. So we could get very, very basic and say, well, we compress air in our lungs and push that into a balloon, right? Well, we have to do that in an industrial way. So how do we do that? The technical definition, an air compressor is a mechanical device that converts power into kinetic energy by compressing and pressurizing air. It sounds pretty complicated, but it's really not. There's some different types of air compressors out there. We're not concerned with those too much today, but an air compressor compresses air, so we can use that to do work. All right. Variable frequency drives. If you see some of the new compressors that factories are putting in place, the VFDs help save a lot of energy. So it produces air when it needs to produce air, and when we have times of break times or shift change, things like that, we don't need that compressor running as full force as it usually is. One thing that's important to note here is air compressors are typically sized using a CFM. It's cubic feet per minute at a specific pressure. Okay, so if you go to Home Depot, Lowe's, any of the big box stores, and you're trying to buy a compressor for your garage, even a little pancake compressor, I have one sitting here that I'm powering this stuff with today. What matters is, what CFM you're going to get at what pressure. That's how much air it's going to compress in a given amount of time to a certain pressure. Okay. Also note that this is a symbol for an air compressor. So that symbol we don't see a lot in that schematic that you have on your front page there. I don't believe that that's on there. We don't typically see that on a schematic. That's something, upstream that we don't normally look at. Okay. But if you do see that symbol there, that is for an air compressor.
One quick note: does NEFF sell compressors? Are we worried about compressors? No, we don't sell compressors. We're everything downstream, and we'll go starting here, right? Air prep.
So anything from here on, we can offer.
Okay.
Okay. So air preparation. No. So a lot of times you're going to hear FRL, air prep or FRL. So you'll have customers say, "I need an FRL package." Okay. FRL can mean a lot of different things, but technically it's filter, regulator, lubricator. Okay. Lubricators aren't used very much in pneumatics anymore. We do sell lubricators. We've got some really large customers, or customers that use a large amount of lubricators. There are applications where we use lubricators, and we're going to talk about those a little more here in a minute. But they are vital to a pneumatic system. So filter, it's going to filter out any particulate, any moisture, anything that's going to harm your valves or cylinders or whatever you're doing work with. So the filter is very important. The regulator, we need to regulate the pressure down or up, depending on our application there, but we need to be able to adjust that pressure to do the work that we need to do. And then the lubricator adds lubrication to the system. Go ahead.
Are most shops that you guys go into, are they a standard PSI 90 or 100?
Typically shop air and is 90, 80. They say 85 to 90. PhD, one thing to note with them, everything they base everything off is 87 PSI for some crazy reason. I'm not sure, but they kind of come up with that number. So yeah, but 80 to 90 PSI is typically shop air. Okay. You will see higher stuff, but it's
yeah, and you'll see sometimes they have their compressor at 120 PSI, but by the time it gets out to the shop floor, you're 90 or 100 PSI, and they're regulating down to 90 or something like that. But it's usually somewhere between.
Yeah. Does anybody know why it's lower pressure? Why lower pressure is better? No. Yeah, cost. Cost is cheaper to make, right? It's very expensive. A lot of people think compressed air is air, right? Compressed air is not cheap. Compressed air is very, very expensive.
So there is a fun fact. There is a little app out there that Parker has. You can download to your phone, and you can put your everything you're using out there, cylinders, grippers, whatever, in there, and adjust the pressure, and it can show you how much you'll save that customer just by adjusting the pressure down from, say they're running at line pressure 90 psi or something like that, but it only takes 50 to 55, 60 psi to do the work. They can actually regulate that equipment down to 50 or 60 psi, and it'll save tens of thousands, if not hundreds of thousands of dollars, depending on the size of the facility. So there's a huge cost there. There are extra items we can add to your FRL package or your air prep package. Those are diverter blocks, pressure switches, safety valves, lockout valves, and there's a plethora of other things. This guy down here, this is, like we said, is product agnostic. This is the Wilkerson version. We offer this. This is actually an SMC, I believe. But you can see how they've got this thing put together. So they have a particulate filter, a pressure regulator with a pressure transmitter, coalescing filter, we'll talk about that, a distribution block, which is just someplace you can, use to, get some air out before we get down to a lubricator. So if some of your things on your system need lubricated, that's fine. Other things you don't want to use lubrication for, so you would put a diverter block there so you can get your air out before the lubrication. Slow start valve, and then we've got a manual shutoff. Okay. There was a question we had on the test earlier on in this training about where we put this manual shutoff. What is proper? Well, there are some, it almost starts a fight when we bring this up. In that picture there, it's at the end. Okay. Do you guys see any benefits to putting at the end or at the beginning of your FRL package? Any ideas?
You're not shutting off your diverter block right now, so.
You're not shutting off the diverter block, right? So if we didn't have the diverter block, what would happen if we need to quick dump this, if we need to shut that air off and lock it out there, if this diverter block or this shut-off valve's out here at the end of this unit, now we can kill it and it's going to dump all that air out from your system. But if that thing is back here at the beginning, now it has to run back through all of your devices and dump. Okay, so it might take a little longer. So the safety, as you guys well know, the safety standards change almost daily. This is one of those things that's starting to take hold. They're putting it at the end of their units. And you'll have some old guys that say, I've been doing this for 30 years, and they put it at the beginning. That's just the way it is. It's really, your preference, and usually almost all the factories now have a safety protocol they follow, and you just have to know what that is. Okay.
There's two things you can see on our demo unit behind Josh there, where our lockout is.
This here?
It's at the beginning, right? They have it at the end. The other one big thing, if you have this lockout at the end and you have a soft start, when you turn this back on, this soft start is already fully pressurized, right? There's no soft start function at that point. So it's another thing. There's a lot of things to think. So you can write this down. We recommend that it's at the beginning for now. I mean, the only downfall of that would be is if you didn't have a relieving regulator, and we'll go through that side. But besides that, always at the beginning.
Yep. So it's just something to think about, and your customers usually know these things. It's a question you can ask, but when we're offering them these devices, they're all modular. So, if we need to swap that and put it at the beginning, it's just two little bolts and we swap it and put it at the beginning. Or put it at the end, we can put it in the middle, it doesn't matter, it's just all modular. Any questions on FRLs? We're going to go deeper here. So we're going to talk about filters. That's the F of the FRL. So our particulate filter, they're the most common types of filters that are used in air prep. They work to trap and retain particles of debris, moisture, and some oils. This is very important. Typical size is 5 micron. That's very common filtration size for a particulate filter. So now we're going to talk about a coalescing filter. Does anybody know what a coalescing filter is? So coalescing filter is still a filter, but it's going to pull out any aerosolized oils and things like that in your air supply. All right. So a coalescing filter, they're not as common. We don't sell near as many of these just because they're not used as often, but they remove liquid particulates, aerosols, and vapors from compressed air. So again, typical micron size is 0.01 micron versus a 5 micron. So if you think about that, very much tighter micron size. So we're going to filter out finer oils and things like that. All right, so if you look at the size, the micron size, the difference, which one would we put first, a particulate filter or a coalescing filter? Particulate. All right, because the particulate's going to pull out most of that stuff. If we have our coalescing filter first, it's going to get bombarded with oils and debris and water, vapors, things like that. So it's gonna get clogged up pretty fast. And then that particulate filter is going to be doing absolutely nothing. We've already filtered out down to 1 micron, and this particulate filter at the end is 5 microns, so it's just not doing anything. Okay? Any questions on that? So if anybody asks you at the end of the training, what's a coalescing filter, everybody can tell me what it is? Bobbleheads? Yeah? Okay. Don't be afraid to ask questions. Regulators, so that's the R of your FRL. So regulator, it regulates pressure of a compressed air pneumatic system to whatever you need to do the work. Okay? So you can regulate that pressure down, you can adjust that pressure wherever you need it. So there's 2 different kinds of regulators, basic regulators, relieving and a non-relieving. Does anybody know the difference in a relieving versus non-relieving? So we don't sell very many non-relieving regulators, but there are applications. I've learned my lesson the hard way, so make sure you guys understand what a relieving and non-relieving is. The relieving will relieve the pressure as you adjust the pressure down. So this is a relieving regulator here. So as I adjust this pressure down, gotta have pressure first. As I adjust it down, you're gonna hear it go tss, tss. You might not be able to hear it, but you can hear it. You can see the gauge moving down. As I adjust it up, the pressure moves back up. A non-relieving, once I have, say I have 50 psi pressuring my system, and I adjust this down, this pressure is not going to relieve. It's not going to move. It's going that pressure from that regulator on is trapped. Okay, so we're not going to relieve that pressure until we cycle a valve, and then that pressure is going to drop to whatever you adjusted it to. Does anybody know why we need a non-relieving? What applications? Any applications? Liquids. I had one recently that they were using some kind of gas. I can't remember what gas it was, but they couldn't just relieve that gas into the atmosphere. It's very expensive, so they wanted to use that gas and make sure that was contained within the system. So they didn't want that relieving as they adjusted the regulator down. So they're not as common, but a relieving regulator is very, very common. 99% of what we sell and what everyone uses in the industry are relieving regulators. And you'll know it right away as you start to adjust that regulator down. You hear the tsh, and you see your gauge drop. Okay?
That's good, Nick. That's really what the non-relieving is for, is like the fluids, right? The media that you're going through it. You just don't want to dispense it in the atmosphere.
So we mentioned lubricators. Lubricators are not as common anymore. All of our pneumatic products that we sell are lubed for life. Okay, so MAC and PhD, like Dave said, we're trying to keep this product agnostic. However, if you understand that it's not just MAC and PhD, it's Pneumatics, it's SMC, it's all the other guys out there, they're all lubed for life. Okay, so whatever life that is, maybe it's 10,000 cycles, maybe it's 1,000,000 cycles, it's lubed, and that lubrication should lubricate that device for the life of its it's rated for. But in certain applications, we need to add lubricators. Anybody know the number 1 application we use lubricators in? Air motors. Air motors, screw driving, yeah, something like that. But air motors, they need to be, that's where they get their lubrication from, is from that air, that lubrication that's in the air. So I'm going to pass around, this is a combination unit. We'll talk about this. This top portion is a regulator. This is a particulate filter. So it's a combination unit. This is a filter and a regulator combo. And then this is a lubricator. So technically, this is an FRL. Okay? Pay attention to the regulator itself, the gauge ports, the modular design, and how you would take that apart. So it's literally one Phillips head screw here, and this thing will slide apart, and we can change the order around. And then there's also arrows on the front and back that tell you which way the air needs to flow through this thing. So pay attention to some of those things. And then this lubricator, notice it has a little knob on the top here and a little fill and we'll talk a little more about that as we pass it around here. So lubricators, lubricators are important to air motor applications, screw driving, things like that, because that's where they get their lubrication from. Do we use lubricators? Can we use lubricators in valve and cylinder application? We can. We have to make sure that thing stays full. So it's very, very common to use a lubricator. Somebody specs in a lubricator, they put it on the equipment, and they fill it up with lube, and it runs dry, and the maintenance crew or the operators, they never look at it again. It runs dry. And 6 months later, they start to have valves that are sticking. They have cylinders that are blowing by and things like that because they wash the lifetime lubrication out of the devices, the valves, the cylinders, the rotaries, the grippers. All that lubrication has been washed out, and now it's running dry, okay? So if we're going to use lubricators, we need to make sure that they stay filled, okay? They never run dry. If they do run dry, we need to get them filled up fast and then keep an eye on valves and cylinders and things like that. So if you have a customer that says, hey, this thing's ran dry for 6 months, we might want to start, hey, Mr. Customer, maybe we need to get you a spare valve, spare cylinder, a spare gripper, something like that, because the likelihood of something failing is higher. The other thing you can do is, you can be a little preemptive and go through those things and re-lube them manually. But typically, whenever you refill your lubricator, it's going to lube those anyway. So we don't typically have to do that. Any questions on lubricators? All right, one last very important detail. If you're using a lubricator, where do we put that in the system? Do we put it before a filter, before the regulator, after the filter, regulator? Where do we put that in the system?
After the regulator.
After the regulator, after the filters, because we're trying to get all the particulates, all the moisture, anything like that out of the air supply before it gets to a regulator, before it gets down line. And then we want to reintroduce lubrication. So we're trying to pull out any aerosolized oils, and then we're going to reintroduce oil that we want to lubricate our devices, right? So that's usually at the end of the line, okay? So it's very important to understand where that goes in the system.
You would put the coalescing filter after the regulator, though?
You would, yeah.
Filter, regulator,
Yep. Typically. You can put it before that, but it probably will end up causing problems with your regulator if you're pumping lubrication through your regulators.
The coalescing filter?
Oh, the coalescing filter goes before the lubricator.
Right, I was just reading your block over it. Seemed like that was the order.
They're pleased.
Josh, you filter,
Yeah.
coalescing filter, regulator, lubricator.
Yeah. Yep. Any other
And
questions?
lock out first. Hint.
Yeah.
Just so you know.
All right, so there's other kinds of regulators out there. Go ahead.
Lubricators.
Mm-hmm.
They be filled while the system's pressurized.
Yes. Yep.
Yeah,
Most. I should say most. All of the Wilkerson ones can be.
backflow.
As far as I know, I think there may have been some SMC guys back in the day that you had to lock them out or shut the main shutoff off before you filled them. But I think everything to this up to this date, I think they're all able to be filled. So we'll talk about different types of regulators. So everybody, I've passed that around. You see that knob on the top, you can adjust your pressure up and down with that knob, okay? And if that knob doesn't turn, by the way, pull the knob up and it'll turn. If you pop it down, that kind of locks it in place. It doesn't accidentally get adjusted. There's other ways to adjust a regulator, okay? Well, we can do that with a pilot air supply, and those are called PORs or pilot operated regulators. So a POR has the same basic function as a standard regulator, that guy I'm passing around, same basic function. Instead of the manual adjusting knob, it's going to use a pilot air source. So where do we get that pilot air source from? We'll talk about that in a second. A POR is great for applications that need the flexibility to adjust the pressure often. So think about this. We're in the business of automation. So we're selling automation supplies. We're trying to think ahead and try to set up a system that doesn't need a lot of human intervention, or at least limited human intervention. So whenever we want to adjust that regulator, we want to be able to do that electronically or automatically, okay? Well, how do we do that? We do that with a PPC, a proportional pressure controller. These are called many different things, IDPs, and we're going to talk about these a little more. But this is a POR, okay? But understand this top port right here, just imagine that'll either have a manual knob on it or it's going to have a port, and we're going to add or reduce pressure. And it's just going to adjust that diaphragm just like a regular manual regulator would do. Your air supply is going to come through this direction. We're going to regulate it down with our knob or our air supply, and it's going to come out this side. Okay, so I'll pass this around. Make sure this gets back up to the front of the room though, because we're going to talk a little bit more about that.
There's a couple things, reasons why we use PORs. Anybody have a good one? The one I see 90% of the time, if there's a machine and you have a knob, the operator, they're going to turn it. If something goes wrong with the machine, they're going to be like, does that help? Does that help? Now this machine's all over the place. Now, because you can mess up your timing, you do all kind of crazy things, especially forces. But a lot of things is you have to do it, you don't want to mess it up. The other thing is you can do it remotely from a panel. You could actually run the PORs with another little mini regulator, right? Just doing an air spring. So that's the main difference is this has an air spring, the other ones have a compression spring. It's the exact same internals underneath, it's just how you control that force on top of the diaphragm.
So how do we control that pressure on the top of that diaphragm? So how do we do that? We can do that with a manual knob and a compression spring like Dave was saying, or we can do that with air pressure. But how do we adjust that air pressure? What do we do? How do we control that? Well, we can do that with a couple different things. The Mac PPC here pictured is a little different beast than this guy. This is, I think that's a Wilkerson. It might be a Pneumatics.
That's Wilkerson.
It's Wilkerson. But these are called I to P's, E to P's, or PPCs. They're called many different things, but all they're doing is electronically adjusting your air pressure. Okay. So PPC uses an electronic signal and it controls a pneumatic device. So how does it do that? Well, we give it a signal and it says, hey, what pressure am I at? So what do we need to have inside of a PPC? We got to have a pressure sensor or a transducer in there, okay? So we need to know what the pressure is, and then we need, what else do we need in there to give it some more pressure? A valve. We need a fill valve. Well, what if we get too much pressure? We need a dump valve. So we have a fill and a dump valve. So there's two tiny little valves in that blue thing I'm passing around there, that PPC. It looks just like this. There's two tiny little valves in there. One's for filling, one's for dumping, okay? There's also a pressure transducer in there because we have to know what the pressure is. And then we give this thing a voltage or a current supply, like a 0 to 10 volt or a 4 to 20 milliamp, and we can adjust that pressure from 0 to 100 psi, 0 to 200 psi, 0 to 30 psi. Whatever PPC you order has a pressure range, and it has either the volt or the current controls. So if that guy I passed around, I think's 0 to 100 psi, and it's a 0 to 10 volt. So if I give that 5 volts, I should receive 50 psi out of it. Okay. Now, is it going to be perfect, exactly 50 psi? Probably not. There's a plus or minus 2.5% miss rate or miss area there, but we can get those dialed down to like 1% or even a little better than that, but they're not very typical. Plus or minus 2.5% is usually where everybody lands. So the reason I wanted to get this guy back up to the front of the room, there's a reason that I have both of these pictured here, okay? This is a little different beast. So Mac's POR or PPC is a little different than the Wilkerson or the Pneumatics or any of the other guys in the market. The reason they're different is Mac is designed to be in a closed loop system. Can you pass that back up here real quick?
Closed volume.
Closed volume. So our air supply is coming in this way, and we just have that teed off, so we're feeding air to the top to our PPC. Out of that, we are going to fill or dump to get whatever pressure, but this is a closed loop system. So it comes out of our PPC into a volume chamber here, and then right into our regulator. So this is a trapped air pressure here, trapped volume of air, and Mac needs that to stabilize. Okay, because Mac is so fast, the good and the bad of that. The good is we can fill and dump very, very fast. The bad is we can overshoot because we're so fast that we can overshoot. So to stabilize that, they recommend having an air volume or a chamber in between so we can stabilize that air, because air is very compressible. So if we just had this thing short nippled to that regulator, there's not a lot of air volume there. There's not a lot of air to compress. So we're going to start motor boating, which is filling, dumping, okay? So with Mac, we need to have an air volume between it, and there's many different sizes. The PPCs for Mac, this is the PPC 5C, by far the most common. They have giant guys out there. I've sold one of them, and I think it was Doug's customer. We sold one of them, and they could have done it with this guy. All right, we're just adjusting a small amount of pressure to a regulator. This regulator can get giant. Okay, we can get this up to like a 3-inch port, so we can flow a ton of pressure, or a ton of flow through that regulator, and still be able to adjust the amount of pressure just with a little PPC 5C on top. Okay.
The key note there is Mac does not control flow. You cannot have an open flow volume through that. It has to be a closed loop, a closed volume system, and then we can control it through a POR, which actually can flow pressure. Right?
Does that make sense to everybody? That's a point of confusion for a lot of people. So if you ever have a PPC application or you need to use a POR, don't hesitate to run from those. We win these every time. I don't think I've ever lost one, just because we can put that little package together for them, and it's bulletproof. Those things run forever.
Some projects are longer than others, right, Nick?
Let's move on from that one.
Yes, I'll talk about that.
Wilkerson and Mac offer PPCs, but there's important differences. We discussed that. Everybody understands the difference, right? Very, very important you understand the difference.
But we do not sell enough of these. These applications are everywhere.
Right
Everywhere.
behind you there. All right. So the one I passed around, that FRL I passed around, had a filter regulator combination on it, like that guy there in the picture. So that one has a combo unit. So what's the benefits of having a filter and a regulator combined? Saves space, saves a little cost a lot of times. What's some downfalls of having a combination unit versus separate filter and regulator?
All that stuff's running through your regulator.
All that stuff's running through your regulator, right? So it'll protect your regulator a little better, filtering that stuff out first. What a lot of, and usually it's the older generation, they liked having a filter, a regulator, and a lubricator, or whatever else in their FRL package. Because if one component went bad, say the regulator went bad, they just replaced the regulator. So it was cheaper to just replace that. Or the filter, That combination unit, if something goes wrong with that, they got to replace the whole unit. So it costs a little more at that point. But a lot of the newer generations are looking at this saying, it's saving me money in the beginning, and the chances of something going wrong are slim. And if I need to replace this thing, it's really not that big of a cost difference to go with that combination unit. Saves me space, I can put one of these things on the shelf, and it's a combination unit, okay? So that's the only reason that they have those things combined. It's just a convenience thing, a space saver. But you're gonna see them both ways, okay? This one up here, this is a combination unit. We use that to save space. I mean, we could have put a whole FRL package on here. And if you see some of the FRL packages on some of the newer equipment, especially European equipment, it might be 12 or 15 units wide. It'll take up the whole back of a machine, all right? And those are usually like Cat 4, Cat 6 rated, whatever it is. And they'll have every little device separated on there, and it'll be in a very specific order to meet that standard, whatever they're trying to meet.
We do a special one here for a customer at Pawnee, and it's a thing, the FRL unit's probably about 6 foot long, Dave. The one for Wayne, and that's huge. It's got to be that long. So.
Yeah, so it can get pretty long. Other devices that we can put in line for air preparation are water separators. Water separators, if you guys know anything about pulse valves or have sold pulse valves, water separators are very, very important. These guys, we sell these guys. These are Tsunamis. They're very fancy looking. Dave actually spearheaded a study here with Parker, Wilkerson Parker, and found that the Parker unit is not only cheaper but much more effective. But there are tons of water separators on the market out there. You see a Speed Air guy here in the middle. There's SMC, Pneumatic. Everybody has them out there. Water separators are water separators. They do just that. They separate water from your air. Okay. So what's the difference between a particulate filter and a water separator? Mainly, we're separating water only. Okay. Particulate filter is going to pull out a lot of the particulate. Now, a water separator will pull out some of that larger particulate as well, but its main goal is to change the velocity, change the direction and flow of that air to let those water droplets either push to the outside edge or fall out of suspension. So it's made for larger water droplets, some larger. So we see that in dust collection all the time because a lot of times you'll have air prep in the building, you'll have air dryers, and by the time the air gets to the dust collector that's outside up on a tower, there's so much temperature differential there that we start to build moisture in the air. And by the time it gets to the dust collector, it's got moist air, and next thing you know, what happens to valves or cylinders that have moisture in the air? It washes that lifetime lubrication away, and they go dry. Okay. Corrosion, big problem. Corrosion. So freezing, big problem, especially in dust collection. So corrosion, I like that you mentioned corrosion. So if we have corrosion, what happens? Well, it clogs up our valves, clogs up cylinders, wears out seals, things like that. How do we get rid of that corrosion? Well, we need a particulate filter in line, but we're already past that point. So that's the issue. Okay, so don't miss water separators. Don't miss FRL packages right at the point of use. I think almost every air compressor out there has a dryer or some kind of way of drying that air, because when we compress air, it does gain a lot of moisture.
Those don't have a micron rating, though, right?
No.
I don't believe. Yeah, I don't think they have a medium.
It's literally just for liquids. Fluid.
Yeah. And if you
we
look
can
into
show, outside, we have a compressor we rented, a large one, and also a dryer, which we can show out in the shop here.
Yeah. And again, that stuff usually isn't shown on that schematic on that first page that I showed you. That's usually not shown. If you ask for that schematic, they probably have that schematic, but that's not what a customer is going to give you. Okay. Other common air prep components, we've got shut-off lockout valves. So this guy up here is a shut-off lockout valve, but it's missing the silver little tab here. This is that silver tab that we're missing. This has been all over the countryside. But that silver tab is very important. Whenever you shut that valve off, you can pull that tab out a little bit and put a lock in it. So that can be a point of lockout for safety. This thing here is just a muffler. Goes in the bottom. You can see it sticking out of the bottom of ours here. And then this guy here, this is a slow start quick dump valve. Quick dump valve. Whoops. So does anybody know what a slow start valve is and what it does? We don't use enough of these.
Slamming on initial startup.
Yeah, it prevents slamming or damage or dropping parts, throwing parts, things like that. So say your equipment's running and all of a sudden somebody trips a light curtain and shuts, hits an e-stop, whatever it might be, and all motion stops. Well, what happened? Well, we cut air supply, we cut any kind of stored energy, we dropped all that. Well, when we turn the machine back on, and that cylinder is sitting there without air on either side of the piston or a gripper or whatever it might be, and we turn that air pressure back on, whenever it comes on in a hurry. So you're going to get this, and that cylinder might go through the wall. All right, it's going to slam. There's nothing to hold it back. We just give it a big burst of energy. Okay, so that might throw parts. It might break your equipment, things like that. A slow start valve does just that. It offers a slower start. So it slowly builds that pressure up until it gets to
about 60% of line pressure.
About 60% of your line pressure. And after it hits about 60% of line pressure, then it goes full on. Now, why would it go to 60 and then just dump you right to 90? Anybody know? Because most equipment is going to move at, you know, maybe it's 10 or 15 or 20 psi, and maybe 10% of your full line pressure. So it's going to slowly build that pressure up, and all your cylinders, grippers, and everything else are going to extend or retract or open or close slowly. And then once we get 60%, everything should be already in its positions, and then we're going to give it 90 psi to get all of, you know, get back up to line pressure. Does that make sense? The quick dump valve, not dumb valve, quick dump valve is very important. Why? Exhaust that air, get rid of stored energy immediately. All right. So if we have some kind of issue, somebody hit a light curtain, somebody fell into the equipment, whatever it might be, we need to get rid of that air pretty fast, so we can do that. The slow start quick dump valves are not considered a safety device. A lot of customers use them as a safety device. We have better items for that are actually safety rated, have redundant valving in it, things like that in it.
That's the big thing you can notice here is just one single solenoid on top. In the safety valves, there's redundancy on the solenoids. There's two coils on top.
So if one valve doesn't get the job done, the next one hopefully will. You know, whenever somebody's limbs or life is at stake, we want to make sure that we build in redundancy. So if some mechanical failure happens with this guy, we have another backup. Okay?
It's always electronically controlled.
It's electronically controlled, yeah. Yep. So pneumatic tubing, and I'll pass this around here in a minute. Pneumatic tubing is an overlooked part of your pneumatic system. How do we get pressure from point A to point B? We can hard pipe it. We can use iron pipe. We can use aluminum piping. There's all kinds of different tubing, hoses, piping. But most common is polyurethane or some kind of plastic tubing. Polyurethane's the most common. Nylon's a close runner-up. I'm going to pass these around, this whole thing around. Don't be afraid to pull these out and look at some of these different tubes and hoses. This is a big portion that we miss out whenever we're talking to customers and things. You know, if we can ask, hey, at the end of the day, I'm quoting you valves, cylinders, and this and that for your system. Do you need an FRL package? Do you need tubing, fittings, things like that? Most of them say add-on is an option. Okay, I can't tell you how many times the customer says, hey, at the end of the day, we're ordering this stuff, and the purchasing says, well, what all do we order? We ordering every line item? They said, yeah, everything on that quote. And they end up buying that tubing and the fittings and everything else. The benefit of that is not only sales, we get some sales dollars out of it. The other benefit to that is we know what they're using in that system, so we know that they're not using tubing that's too restrictive or that not the correct tubing for the application, things like that. Okay, so I'll pass this around. But understand there is a lot of different types of tubing out there. The most common is polyurethane. So that's what this stuff, all this tubing that we're using today, this is all polyurethane tubing. Has a pretty tight bend radius, and we'll talk about that a little bit. Nylon tubing, has anybody sold nylon tubing or have customers that use nylon tubing? So nylon tubing is good if you have repetitive bending, things like that. If you're running that through a raceway or a wire track or something like that, nylon tubing is far superior to polyurethane. Okay, polyurethane's a little softer, has a nice tight bend radius, but it does, you know, you can wear through it pretty easily. Okay. So, yeah, that's a Freeland Wade sample pack, so that's not tubing. Now, one thing that we need to really watch for, and this is one of those benefits of offering tubing to your customers, you know the application because your size and valves, cylinders, and you're selling them those components, right? So what kind of tubing do they need? Well, if there's any kind of chemical or hydraulic oil, or if this tubing is going to get sprayed with coolant or something like that, or could get sprayed with anything, now we can offer them the proper tubing for that application. If we don't offer that tubing out of the gate, they might use a tubing that's not compatible, and it creates a pain point for them. Okay, so why not pick up a few extra sales dollars and help the customer? At the end of the day, you want to be a solution provider, not a problem point. Okay. what's running through the tubing is very, very, very important. Got to make sure we have compatibility there. Also, what that tubing is coming in contact with, or a lot of times that tubing will lay in a place where it's going to have oil. It'll be laying in a puddle oil or something like that. We just need to make sure that we ask those questions, or at least look at that stuff when we're looking at an application. Okay? Questions about that? So, pneumatic tubing connection types. Most of these tubings we use are push to connect. They call them PTC. Everything on the board here is push to connect. So if you guys come up here and play with this, they're all push to connect. Does everybody know what a push to connect fitting is? You literally push that tubing into that fitting, and it grabs it. I'll pass this around. You literally push that tubing in, it'll grab that. Whenever you want to release it, you pull back on the plastic little ring here and push the tubing in slightly and pull the tubing out. Okay? But those are push to connect fittings. Barbed fittings are on the right hand side there. Barbed fittings are used whenever tubing gets very, very small or in hose applications. Okay? Barbed fittings are, just that. They have a barbed connection point. You slide that tubing over it. We wouldn't use barbed fittings if we're using very stiff or a high durometer tubing or hose. So it needs to have, it needs to be designed to be used with barbed fittings.
Barbed fittings you'll see a lot in medical applications, a lot.
Medical, and if you're missing your medical applications out there, guys, don't visit those guys. Tubing, fittings, there's a ton of work out there, and if you can offer a solution, and with the tubing package I'm passing around there, we have solutions for all those.
Why barb versus push to connect?
In medical, typically there's very, very soft tubing. It's super, super soft for bend radius and stuff. A special kind of tubing. Further than Wade, we talked about the tubing. They make a special tubing for the medical industry. Don't sleep on those sales. Some of those customers buy millions of feet of tubing a year. So,
literally millions of feet
millions
of tubing.
of feet.
Compression fittings, that's this guy here. They have a little ferrule you slide over top your tubing. Nut goes on first, don't forget that. Slide the ferrule over, push that in there, tighten it down, and it actually crushes that ferrule, pinches the tubing. And then you've got DOT fittings. DOT fittings can be plastic or some kind of metal, usually bronze or brass. But the plastic, a lot of people say, well, if it's plastic, it's not DOT. That's not true anymore. DOT fittings can be plastic. The main difference between DOT fittings and push-to-connect fittings is they usually have a tube inside there that slides in the ID of your tubing, so that tubing can't compress too much, and we get a positive pinch on that on the tubing itself. Whenever there's a semi going down the road and they're using air brakes, we want to make sure that tubing's got a good solid connection. It's not going to blow off, things like that, because
You'll see a little brass ferrule internal.
yeah. All right. Any questions on fittings? Don't sleep on these. So a point of contention, threads. What threads are compatible with other threads? One thing I will tell you guys is look at your catalogs. Legree catalog, the first couple of pages of the Legree catalog has, I think this was pulled from the Legree catalog actually. Piab, they have a great one in their catalogs. Bless you. And so NPT is National Pipe Tapered. A lot of times it's National Pipe Thread, but it's important to add that tapered because it is a tapered thread. It does, whenever you tighten that thread down, it's going to tighten on that taper. So we need to use pipe dope, pipe tape, some kind of sealant on those threads, okay? That's very, very, very important. You'll see a lot of customers that don't use that stuff, or they'll reuse pipe tape, and it's a point of leak. NPS, National Pipe Straight. So instead of having that taper, it's the same pitch, but it's a straight thread, okay? You're going to see a lot of times NPS threads will be used in vacuum, and they're compatible with G threads. So you'll have a NPS female connection, a female thread, and then you'll have a G thread that is the male that comes down and seals on that because it has the O-ring seal.
The number one use for NPS, the pipe straight, is conduit connections. Right? If you see in the end of the Mac manifolds, the conduit, any conduit connection is definitely an NPS straight thread.
Yeah. G thread, my favorite thread. I think everybody's favorite thread. That's this guy here. So it has a straight thread and it has an O-ring seal on it. So you tighten that down, crushes the O-ring, and it creates a positive seal. Why would that be our favorite?
2 reasons.
There's a few different reasons, yeah.
Don't need thread sealant.
You don't need thread sealant.
Yeah.
Easy to install. And that height, whenever it comes down and bottoms out, it's a positive stop. So that height never changes. So we use this a lot in vacuum and vacuum cups, things like that. Can you get vacuum cups with MPT or MPS? Yes. But 99% of them are G thread because once you tighten that cup down, that height of that cup or the depth of that cup is the same every time. Okay. Then we have BSPT. This is a British standard, and it's just a taper thread. It's very similar to the NPT, but it's the British standard pitch.
You're referring to the actual overall height.
Overall height.
The G thread compared to the effect that it has in the system.
Exactly. So that G thread, when you tighten it down, it's the same every single time. Okay.
It's very important on end-of-arm tooling for robots, right? If you have an NPT thread, that maintenance guy cranks it in there and it cranks it all the way up. Next guy just hand tightens it on there. It's all over the place. So now you got to adjust your robot.
Yeah. You can get up to a 1/4 inch, depending on the size of that thread. You can get up to a 1/4 inch difference in height, just by, Dave. He's tougher than I am. He can crank them down, and I'm sissy. I'm just barely putting these things in there. They're not leaking. Neither one of them are leaking, but now we've got a big difference in height. Which ones are compatible with one another? There's a couple different things you can use. Look at these charts in your catalogs. It'll tell you. I have customers that say, listen, if I have an NPT female thread, I can put a G thread in that and just crank it down until it's tight and it won't leak. Well, you're right, if you tighten anything down, but it's not the proper way to do that. It's not the right pitch. It's not the right thread for that hole. Okay, so there are some threads that are compatible, and there are some threads out there. They're called uni threads.
Like a universal version. Yeah.
Universal threads. Don't recommend those. They don't have a lot of thread engagement, so depending on the female thread, if you over tighten them, they'll actually strip the threads off. I don't recommend those, but they're out there. You'll see them. Flow controls and needle valves. I thought I had a needle valve. Does anybody know what a flow control is? Self-explanatory. It just controls the flow. We're going to talk a lot about flow and pressure here today. So a flow control, I've got flow controls on the board here. So these guys here, they have a little knob on them. You can adjust that flow. Okay. So these are flow controls. You can do inline flow controls. And there's many different types of and shapes and sizes of flow controls. What's the difference between a flow control and a needle valve?
Needle valve restricts flow both ways.
Both directions. So I'll pass this around. This is a very tiny needle valve, but this actually will adjust flow in both directions. So it's going to restrict the flow this way and restrict the flow this way. That's a needle valve.
Do I get the draw now, Josh?
Yeah.
All right. My favorite. So we'll talk about some schematics here real quick. Anybody know what that is?
Flow control.
No. Restriction, right? It's an orifice, some type of orifice, right? Could be anything. Could be a pinhole to 4 feet diameter. What's that, Doug?
That's adjustable. I know.
That's adjustable. That's a flow control, right? That's what that means. That's all that's doing is now you have an adjustable orifice. You can control the size of that orifice. That's really all it is.
So if you guys go back to that first page and look at that schematic, you can pick out where the flow controls are. Now that he's drawing that, you can find those in your schematic.
Yep. So now, like Doug said, this is bidirectional, right? This way you can flow this way, you can flow this way. Doesn't matter. Still same orifice on both sides. You still have the same pressure drop. Doesn't matter. Anybody know what this is? Check valve. And we'll talk about those in a little bit, right? That is not bidirectional. It's unidirectional, right? So you can flow this way. Air pressure will push off you. Sometimes you'll even see a little spring back here. So this ball is sitting against the seat. It should be touching it, actually. So you can flow this way, the ball sits against the seat, and you can't flow backwards. Anybody know what that is? Yeah, what's it called? Yeah, what's it called? This is a flow control, right? This is the flow control. The other one's a needle valve. This is the flow control, because now you have full flow this way, right? If you're coming this way, you got full flow coming because you're gonna have restriction, but you can also flow around. You can bypass it, right? When you're coming back, now this still checks off, so you only have through the orifice now, right? Through this variable orifice. So now you have that flow meter out. So you can flow in, but you can meter out. And remember that, when in doubt, meter out. We'll talk about, I think, full flow.
When in doubt, meter out. If you
Very,
don't remember
very
anything
important.
else today, when in doubt, meter out.
That's a good one. Yes, that's very, very important.
If you look at your Legree catalog, any of the catalogs out there, all the other fittings out there, they offer meter in and meter out. And I think I've sold 6 meter in flow controls in my 8 years at NEFF or whatever it's been. It's
Typically,
always,
those are just the control air motors, the
Yeah.
speed of air motors. That's really all.
Yeah. So we don't want to. Does anybody know why we don't meter in? We wouldn't want our metered flow going into our cylinder. Does anybody know why? Smoother motion because. Right, because air is compressible. All right, so if we're metering this flow into this, we've got the tubing, the air that's in our tubing. That's the only air we have that's compressible. Well, what happens once it gets in here and gets to the point where it gets this piston to move? What happens when that piston moves? That area changes. Pressure times area equals force. I'm going to drill this in your head today. Pressure times area equals force. When that area changes, what happens to the pressure?
Volume changes, Josh, not area.
The volume changes. What happens? Pressure's going to drop. So now we drop. So we get enough pressure to get this thing to start to move. So it's going to say, oh, there's a lunge. But now that volume has changed. So now what happens? Pressure drops. Now we're below the pressure to move that piston. So now we got to wait for it to build back up. So we're still metering in. What's going to build that pressure back up, and it's going to lunge again. All right? Now, this is all going to happen pretty fast, but it's going to be bloop, 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 bloop. Okay? That's why we don't meter in. It's going to be this real jerky action. It's very, very hard to get anything to smooth out. Like Dave said, meter in is great for an air motor because there's the same volume of air. We're metering how much flow goes to the air motor, so we're adjusting the speed of the air motor. That's it. So we can meter in there. Metering out allows us, so if we're metering out here, now we've got all of this volume in here that is compressible. But we're giving it, say, 90 psi, but we can only get X amount out of that flow control at once, at any given time. So now that air is just compressible, so it's just going to be a, okay? So there's none of that herky-jerky stuff. Does that make sense? Questions about that? So when in doubt, meter out. Don't forget that. Difference between flow controls and needle valves. Everybody clear on that? Everybody clear on what Dave drew and how that ball check works? And if you look at any of your flow controls out there, they'll have a schematic either in the catalog or a lot of times right on the side of that flow control, and it'll tell you. And if you can look at that schematic, you can tell whether it's a meter in or meter out. So a lot of times they don't have a part number on them, so you can't really look it up. But if you have a customer that's having problems with herky-jerky stuff, you can usually look at that schematic on the side of that flow control, and you can tell if it's a meter in or meter out. All right, check valves, which we talked a little bit about now, versus pilot-operated check valves. We don't use pilot-operated check valves as much as we should in pneumatics. What is a pilot-operated check valve? I think we know what a check valve is. Everybody clear on what a check valve is? It's going to, any flow going this way, it's going to push that ball against the seat, and it's going to shut that flow off. Nothing's going to get through. Flow coming down here is going to push that ball off the seat, and it's going to flow around that, so you're going to get flow. So a check valve, it's just like a diode. It's going to allow flow in one direction, but not the other, similar to a diode.
One note, I think Josh learned his lesson this year about check valves are rated by cracking pressure, right? So you'll see some places in a catalog, someplace somewhere it's going to be on it. It says cracking pressure. So there's a minimum operating pressure. So all that means is the force of that spring. You need 1 psi, a half a psi, 10 psi, whatever it may be, to open up that check valve.
Yeah, and it can burn you. Trust me. Like I said in the beginning, I'm still learning too. Pilot operated check valve is a little different beast. What happens with a pilot operated check valve is we still have our regular check valve here, okay? But we add a pilot source. See that little line on the right side there? That's our pilot air source. So when we have that pilot source, it's going to shift this over and allow flow. All right, so that's kind of confusing. But we're going to have a basic ball check in there. It's going to check the flow in one direction, not the other. But if we add a pilot air source and shift that valve over, now we're going to free flow both directions. So it's just basically a valve. One side of it is a check, the other side is free flow. So we're going to look at applications about that. Everybody kind of understand that? We'll go deeper. But if you have questions, ask them now. So a pilot operated check valve.
So we're just switching between flow control or full flow.
Exactly.
Well, it's not flow control.
Maybe not flow
It's just,
control.
Yeah, it's just checking
Check
or full
valve.
flow. Yeah.
Yeah, it's not adjustable.
Not
There's
adjustable,
So pilot operated check valves, we're going to talk about applications where we use those, where we should use those, and places where it can save us, get us out of a pinch. Okay. Pneumatic tubing tips. Bend radius. Does anybody know what a bend radius is? So if you took that tubing and bent it, how far can we bend it before it kinks? So that's pretty tight, it's starting to kink right about there. So whatever that radius is, that would be the bend radius for that tubing. Okay? Everybody clear on that? Stiffer tubing has a larger bend radius, means you can't bend it as far without it kinking. Once tubing kinks, a lot of times, polyurethane tubing is pretty soft, so if I kink that tubing all the way over, it comes back pretty much 99% or so. If you did that to nylon tubing or any of the polyethylene tubing, things like that, it is going to leave a kinked mark in there, and that is a point of flow restriction. So we don't want that, especially in vacuum. We don't want any flow restriction in our tubing. So if tubing gets kinked or bent, it needs to be replaced, unless it's polyurethane or the kink comes out. Tubing measurement and sizing. Tubing is measured on the OD, the outside diameter. Does everybody know that? So if you order 1/4 inch tubing, this is 1/4 inch tubing. It's measured on the OD, so it should be 1/4 inch on the outside diameter. What about the inside diameter? Does anybody ever look at that? You should. The big difference is if you have thicker tubing wall, you have a smaller ID, which means you can flow much, much, much less. It's a huge difference. So if flow in your application matters, we need to make sure that we're maximizing that ID, but you don't want to get your wall too thin to where it's, weak. So there's usually two options, with like 1/4 inch tubing. You've got a 1/4 inch ID and an 1/8 inch, or a 1/4 inch OD and an 1/8 inch ID or something like that. And then there's an option with a little bigger ID, a little weaker tubing. However, you get a little more flow out of it. Okay.
Typically what we see is due to flow because of such lower pressures, but they do make high or thick walled tubing because of pressure, right? You can get some higher pressures. They make some nylon tubing up to 500,000 psi.
Yeah. So tubing's measured on the OD. Metric and standard size rounding. So there are some tubing sizes that are very, very close to from standard to metric, so they use the same size, same tubing for it. Example, that's 4 millimeter 5/32. So if you see that 4 millimeter 5/32, this little red tube is I think it's 4 millimeter, but 4 millimeter 5/32 are interchangeable. So that means that our fittings are also interchangeable. So if you look at any fittings out there, they're typically, even if they say these are 4 millimeter fittings, if you look at the 5/32 version, it'll be the same part number, or vice versa. So they are the same size. Another one is 5/16 and 8 millimeter. Those typically use the same fittings, same tubing size. So if you have a customer that says, hey, I need tubing fast, and you don't have 5/16 tubing, maybe you have 8 millimeter tubing in stock that you can sell them instead.
And 6 millimeter and 1/4 inch are not the same. You can do it once, but you're never
Yeah.
getting it out of the fitting. So.
Yeah.
Or it'll blow out the other way.
Yeah,
So.
I taking my demo kit around. I do that all the time. You know, typically PIAB comes in with 6 millimeter fittings in all my demo units, and I'm trying to put a 1/4 inch. And like Dave said, you can get in there once. If you get it in there and get it sealed, you're not getting it back out typically. One point I wanted to make was tubing's measured on the OD and hose is measured on the ID. Why is that? Tubing's measured on the OD because we use push to connect fittings, right? But how do we typically use barb fittings on hoses? If you're using hosing, it's usually measured with the ID, so they'll give you an ID measurement. 1/2 inch hose would be a 1/2 inch ID. The OD would be larger, whatever it might be. So that's very important. So if the difference between tubing and hose, there's not a lot of difference, but one's measured OD, one's measured ID.
It does matter whenever you're in a system because it's a lot different in flow, right?
Yeah,
A lot
big
different flow,
difference.
exponentially.
Tubing colors, there's a lot of different options for tubing colors. As I passed that little sample kit around, there's tons of different colors in there. Do we care? I mean, all my tubing that I have is black except this little stuff, and I just had that in scrap. But most of my tubing I just order black. Why does it matter? Anybody know? Why would it matter? Why could it matter? Why should it matter?
Can maybe help you identify your circuit where
Yeah.
things are wrong.
Yeah, so if you have a circuit that has vacuum and compressed air, you know, how do we tell which is which easily and quickly, especially for someone new or someone you're training or something like that? Well, you can color code those things. So a lot of times red will be your pressure side and blue will be your vacuum side, or vice versa. Anyway, there's a lot of different color options out there. There's also rib tubing that has 4 or 5 pieces of tubing bound together, kind of molded together, and those can be different colors as well. And you can kind of tear those apart and use them different ways. There's some customers that are very, very, very particular because they're building equipment that they're selling all over the world, and there are standards in Europe that vacuum has to be X color and pressure has to be another color. Does that make sense? So colors can really matter, and we can do a ton of different colors. We can also do a lot of different custom things too. If you need custom tubing, coiled tubing, rib tubing with specific colors, we can do a ton of that stuff through Freeland Wade. But understand that tubing color does matter. I just use black just because that's what I typically have laying around. But a lot of customers really care, and they don't want everything just to be black tubing because they want to know this goes where and whatever. Okay. So we're going to talk about valves. This is probably the most important thing in this whole training. Valves are not hard to understand, but they can confuse, especially new people, and even some of our veteran people. Okay. A valve is a mechanical device that controls the flow of fluid or gas in a pneumatic system. Pneumatic valves can be configured in many different ways. However, knowing some basics will make the rest easy. That couldn't be a truer statement. All right. So, does anybody know what a single solenoid valve is? Has one solenoid on it. Can a single solenoid valve be a 3-position valve?
Yes.
No. So, 2-position valve. Can a 2-position valve be a double solenoid valve? Yes. All right. We're going to talk about that. So if you're confused, don't worry. So we've got 2-way, 3-way, 4-way, and 5-ported 4-way. Does anybody know? Whenever I say a 2-way valve, do you know what that 2-way means? Not necessarily. There's 2 ports. So if they say it's a 2-port valve or a 2-way valve, they're talking about the same thing. Okay? So there's 2 ports. 3-way would be 3 ports. 4-way would be 4 ports. And a 5-ported 4-way really confuses everybody. That has 5 ports, but it is only 4 ways. Why? Does anybody know? It has separate exhaust for each cylinder port. Good job, Doug. So, so this guy here, cylinder port A, cylinder port B, each one of these has its own exhaust. That would be a 5-ported 4-way valve. Still a 4-way valve. We're still 2 cylinder ports, an inlet, and an exhaust, but we just split that exhaust off, make them independent. So to make things even more confusing, and don't panic, this is a 5-ported 4-way valve on a 4-ported base.
Well, don't worry. We're gonna go through all this. Relax. Yeah,
We'll draw it out.
we'll draw it out. You'll see.
But this valve here, if you look at the base of that valve, there are 5 ports in the base of that valve. So the exhaust is separated from cylinder port A, cylinder port B. They have their separate exhaust, okay? But because it's only one valve on a single base, it just has one exhaust. We don't need that separate exhaust. But that same valve put in a manifold like this manifold could go up to 32 valves long, single solenoid valves. Now, we might need that extra speed to be able to exhaust independently from, cylinder port A, cylinder port B. So that's why they do that. Don't let that confuse you guys, and don't panic. 5-ported 4-way, Dave will make it so stupid clear for you that you'll be enlightened, trust me. Single or double solenoid valve, that just refers to how many solenoids are on the valve. This is a single solenoid valve. If it had another solenoid over here, that would be a double solenoid valve. Direct versus pilot operated. This is a very important distinction. This is a direct operated valve. It has a pilot, or the coil on top, and it's directly operating your poppet. So it's opening and closing that poppet. So if I needed to use one of these guys, I need to flow this much, why wouldn't I just use a direct operated valve for that instead of a pilot operated valve? Anybody know the difference? I don't expect you to.
For wattage, number one, you need higher watt.
You would need a giant coil to be able to flow the 1.2 CV that valve will flow. You need a giant coil. That coil will be this big to try to get that thing to move enough to allow the amount of flow we need. So typically, direct operated valves are smaller flow, smaller valves. So I'll pass this around. This top portion here, you've got your connector on it. This is your solenoid, your coil, and then your poppet in there. And you can kind of look in there and see that little poppet. That's a direct operated valve.
Can I start doing my thing now?
Not quite.
All right.
Internal versus external pilot. So internal pilot means that it's getting its pilot source from our inlet. So this is our inlet. So it's going to tee off in here, and it's going to actually use that air pressure. It's going to tee that air pressure off and use that to pilot our pilot valve. That way we can shift our main spool. This will all become clear in a minute. External pilot. So if we need an external pilot, we can plumb an external pilot source into this, which is just the same line pressure you're using, and that will be our supply for our pilot to make sure our valve can shift. Why would we ever need an external pilot?
Running low pressure.
Low pressure or vacuum if we're running negative pressure, or we're below the minimum operating pressure. So that's this guy, the minimum operating pressure of that valve. Do direct operated valves have a minimum operating pressure? They don't. Why? They're directly operating that poppet. They're pushing or pulling that poppet up and down. So they don't need air pressure. We're not using air pressure to move that poppet. On these bigger valves, we're using air pressure to supply that pilot valve to be able to move the spool back and forth. If we don't have enough pressure, it will not move. So if we have 10 PSI, this valve will have a minimum operating pressure of, say, 25 PSI. So we have to have above 25 PSI. So if I only have 10 PSI I'm using in my system, does that mean that valve's out? I can't use it? Well, no. We just need to supply, 50 PSI to our external pilot, and then the valve will shift and work just fine. Okay?
50 or 15?
50. Yeah. So you got to be above your minimum operating pressure. So that's the minimum operating pressure, and we'll talk a little bit more about that. We're going to talk about all the rest of this stuff here. I'm going to let Dave teach us schematics. All right, so now we're going to talk about the 2-way, 3-way, 4-way, 5-ported 4-way, things like that, and you're going to understand. And while he's doing this, take some notes, ask questions, and then if you have a chance, look back to that first schematic, that page number 1, and try to look at those valves and understand what valve is what that he's teaching. Okay?
Like Josh said, that first page, we have that on the first page for a reason, right? It's the most important part of this entire training. If you guys get nothing out of this, learn how to read the ISO schematics. I promise you, this will help you. We're here to gain credibility in front of your customer. This will do it. This is how Josh and I, why your customers call us all the time. So, ISO schematics. Anybody know what that is? Sorry for you guys over here.
Very poorly drawn box.
Boxes are three-dimensional, Jeff. Pretty simple. It's a square. It's a square. Doesn't mean anything, right? Once we put them together in ISO schematics, these are positions now, right? You can't have a one-position valve. There's really no such thing as a one-position valve that I'm aware of anyway. So these are positions. Position 1, 2, A, B, whatever you want to call it, doesn't matter, right? So now we put some notations internal. Does anybody know what that is?
Two-way.
Two-way. Two-way.
Why? There's 2 ports.
2 ports, right? 2 ports, two-way, 2 position, right? There's 2 positions, 2 ports, or two-way. Any place on the X, or I'm sorry, any place on the square that it touches in each position, right? There's a position here, sorry. Clean this up. In one position, any place it touches the box, right? Or touches the square, sorry, I've got him in the box now. Touches the square is a port or a way, right?
But why isn't that a 4-way then?
So it's one position.
Just in
Just
one position. Does everybody know that?
Each
Everybody understand
position
that?
is independent of each other, right?
So we're just talking about one of those, the lower box or the top, lower square or the upper square. There's two places where it touches, okay?
Yep, it's right. It's either blocked. You can't. There's, your pressure. Put a. This is something for pressure, right? You have pressure on this side. Actually, we'll put it. Oh, man, give me that eraser behind there. It's behind that board there. This thing's terrible.
I don't see an eraser.
It's on the board. It's right in the middle. So that's just inlet pressure. It's not dictating any type of pressure or what the pressure is. It's just pressure, pneumatic pressure. If this triangle was filled in, it would be hydraulic, but it's a different scenario. Does anybody know, is this normally open or normally closed? Who said that? Closed? How do you know that? Yeah, I probably shouldn't have drawn that yet. Now is it normally open, normally closed? Don't know, right? There's nothing that tells us there's anything there, right? Spring, add a spring, right? Now, is it normally open or normally closed? Normally closed. Yeah. Anytime there's no operator up here now, right? To help this position, to move it to that position, number 1. 2, always a manual actuator will take over, right? A mechanical spring will take over. The other way we kind of tell which one is the normal state will be, you'll see the port notations, right? Port 1, port 2. You'll see a lot of things, and Mac does some crazy things. The inlet ports, they can be notated as a P for pressure. You'll see a number 1. You'll see an N for inlet. There might even be a couple more, but what we're here to talk about today is the ISO schematic, the International Standards Organization, and they use numeric, right? So we're going to talk about only the numbers. So inlet is 1. Working port or cylinder port, so it's doing the work where it's going out to, is a 2 on a 2-way. It could be a 4 on the 4-way, and we'll talk about these. And exhaust ports are 3 and 5. So this is a two-way, normally closed. Josh talked about direct acting and indirect acting, or pilot operated. Does anybody know what that symbol is? Solenoid, right? It's a solenoid. So is this valve direct acting or indirect acting? Or pilot operated, what do you want to call it? Direct acting, right? Because you actually, the solenoid, like Josh passed that little 45 series around, the solenoid is actually pushing on top of the poppet. It's physically touching it and pushing it. There's no minimal operating pressure, it doesn't matter. You're just using the power of the coil to move that poppet. So it can be vacuumed to 150 psi, 200 psi, and it will still flow through here, right? If we do this, this makes it pilot operated, right? That's the symbol for a pilot underneath the solenoid. So now you actually have another solenoid, a little pilot valve, operating another valve, kind of like that 92 series. Josh, show them the, see there's one, this is the main valve. This would be like, say this is that two-way valve. I know this is a four-way valve, but this would be the two-way valve. This is a pilot operated valve. So there's a valve driving a valve. Make sense? That's why we need a minimum operating pressure, because there's something, the one valve is pushing air on the side to move the spool back and forth. Right? So everybody gets that? And then when you read these, again, it's normally closed because you have the mechanical spring takes over this square, right? If you energize this coil, all you're doing is moving this square down to here. There's some cool animations out in the field where you can actually draw schematics and systems, and now actually the valve, this little schematic will move down and everything, or you can just move the numbers up, right? So now this is energized. You have flow from 1 to 2. Does that make sense? That's the most basic valve that we deal with that you're going to see out in the field. That could be a butterfly valve, all kind of crazy stuff out in the field even.
So it's never going to be both, you know. So it's only going to be this position or that position. Yep. This would be our energized position. This would be our de-energized position. Is everybody clear on that? So backing up just a second, looking at this schematic now. First thing, customer shows you a schematic and says, "I need this valve." What's the first question first thing you're going to deduct from this picture? Is this a 2-position or a 3-position valve? 2-position. It's got 1, 2 positions. Is it a 2-way, 3-way, 4-way, or a 5-ported 4-way valve? 2-position valve, or a two-way valve. So it's a 2-position, 2-way valve.
You'll still see something like 2, 2, and C. 2-position, 2-way, normally closed.
Okay.
Now back up a little bit, does Mac make a 2-way valve?
Well, kind of. You could plug a 4 and a 3-way.
That was true up to a few years ago. Pulse valves. And there's one more. Come on. #1 seller at Mac.
Dave's favorite.
My favorite. Bullets. Bullet valves. They make a bullet valve and the pulse valve in 2-way. It's the only 2 valves that are true 2-ways for Mac. Like I said, up to a few years ago, they did what you guys did. So they took a 3-way and plugged an exhaust port and made it a 2-way.
That's where the pulse valve came from.
Yeah.
They plugged that exhaust port and made it a 2-way.
Yep, exactly.
Yep.
So that's two-way valves. Very basic, easiest ones to understand. Does anybody have any questions understanding that? Good? Go. Again, 2 positions, right? 2 positions? What's that? 3-way. 3-way what? How many positions? 3, 2. So we have a 3, 2, because right, we have 2 positions, 2 squares. We have 1, 2, 3. 3 places that's touching the box, right? Touching the square. Damn it, Jeff. Right? Put a little solenoid on top here. Is it normally open or normally closed? Kind of don't know yet. We really don't have the numbers, right? We don't know what the ports are. So You look on the little thing up top there, the cylinder working port. Now is it normally closed or normally open 3-2 valve? Normally closed, right? The one port's the inlet, right? So again, we have the normally closed NC. So this would be your pressure port coming in. De-energized position, mechanical spring always takes over. So this is the position you're in. You energize it. These numbers, this pressure shifts up to this port. Kind of pressure comes here. Whoops. Out 2, 3 is blocked. Your exhaust is blocked. So now you're flowing through. What is the major difference between a 2 and a 3-way? The exhaust port, right? So you're filling. Say you had a balloon. We talked about those closed volumes. So on a 2-way, you energize it. Air flows through the valve. It fills the balloon. You de-energize it and shut it off. What happens to that balloon? Stays filled. There's nowhere for the air to go, right? So we use the 3-way. When you de-energize it, now the balloon exhausts the atmosphere. Make sense?
Same thing with the cylinder.
Same with the cylinder. Single
A
cylinder.
single operating cylinder. It extends, but we need a place for that air to go. So it's going to exhaust. You'll hear it exhaust through the valve. Hear that? It's exhausting back through this number 3 port. Okay. If that exhaust wasn't there, if I plug that, it doesn't retract other than it's leaking by my finger. But if I plug that, it has no place to go, so the balloon stays filled or the cylinder stays extended. Does that make sense?
Some type of flow control on an exhaust port.
We'll get there. You're thinking ahead.
Yep.
I like it.
So that's 3-way valves. Is there anything else we want to go through with 3-ways? Same thing with the
No.
top with the pilot operated. I'll just draw it again, but again, that one was a direct acting. This is a pilot operated, right? This is the pilot port. This is the solenoid.
But why would we have a 3-way that's pilot operated? Does anybody know? Same reason that we have a 4-way that's pilot operated. We need more flow out of it.
Yeah.
You know, we don't want our coils to get this big and, you know, sit there and cook all day because we need that much power to shift that thing that far. So we use air pressure to do that. So we pilot operate that thing and we use air pressure to shove that spool back and forth. So we're talking the big 57, 58, 59 series valves, you know, 2.5 inch port. That thing would have to, you know, that spool is going to have to move an inch or something like that, you know. To get that to happen electromechanically, it would take a giant coil to produce that much magnetism to pull that spool and push that spool back. Okay?
That's the primary reason for pilot operating these valves.
Anybody know what that is? What's up? Double pilot operated 3-way, yeah. It's a double solenoid. Called double solenoid, not double pilot operated, but double solenoid valve. Right? Now on a double solenoid valve, what is the default one? Depends where it's energized, right? I mean, we can even put these on here, but it really doesn't even matter because we don't know that last state where it was at, right? So there's no mechanical spring to take over. Does anybody know why we use double solenoid valves? There's two main reasons.
Maybe like a gripper application or clamp or something where you want it to stay in the last.
That's one of them, right? What happens with a spring on this bottom, and this is energized, and say you lose power or pneumatic pressure or anything, it's going to shift back to the original state, right? Because that mechanical spring always takes over. On a double solenoid, if you have this energized and you lose power, it stays in that last state. So when you fire your machine back up, it's back in that last state where you're at, or you energize the pneumatic system, it's back in that last state. There's one more reason we use double solenoid valves. And we don't use them enough in this reason, I don't think. I don't know why programmers maybe don't understand it. I think it's probably the main reason. But anybody else know?
So you know where the valve's at.
That was the last one. Yeah, you know where that last state is. This one is power consumption. You energize this valve for 20 milliseconds, it shifts into this position, you de-energize it, it will stay in this position forever. I don't care how bad you shake it, move it, pound it, it's not moving, right? It stays in this position. So what you'll see is like let's talk a programming error where programmers like to hold this energized for some strange reason. I don't know why. You don't need it. You literally shift it for 20 to 50 milliseconds, it will stay here forever. So it's a big thing with power consumption. So it's a selling point really in some of the systems. You can help the engineers out understand that stuff. So that's the three-way normally closed. I'll show you the three-way normally open just so we have it. And this goes to, again, in its de-energized state, it's a spring. 1 is flowing to 2 with no power, no energization. You energize it, 1's blocked, 2 exhausts to 3. Make sense? It's just a different style of valve. With three-ways, I think Josh has a slide here. There's 5 or 6 ways, or five or six different ways you can use, now not ways as in a port, right. The ways you can use a three-way valve. Normally open, normally closed. You can use them as diverters, right? So if you put, since this is direct acting, if you put the pressure on this port, right? Now you have pressure going out 3, you de-energize it, pressure goes out 1, so you have a diverter. You can use it as a selector. You can put pressure on 3 and pressure on 1 and select the pressure that goes out on 2. So they're called universal valves. If I forget some of the other ways you can use it, not typical. Those are the typical 4 that we use. But that's just so you know, they're very universal in the plumbing. You can use them only in the direct acting versions now, if I'm wrong. You can use them if you have the pilot operate external pilot. We haven't gotten into the external pilot yet, but we can talk about that in a little bit. Cool. So everybody has 3 ways? Questions? No? No questions? Cool. All right. That's not very, need a little more room than that. A little bigger. 4-way valves.
So while he's drawing that, how many positions do we have? 2. So it's still a 2-position valve. So we haven't gotten a 3 position yet. So 2 positions, and we're just adding ways. All right. So how many ports
these ports
are
up
going
here.
to touch? So when a customer hands you a schematic or says, "I need a 4-2 valve," you know what they're talking about. There's still a 2-position valve, but we need to know how many ports they need.
Okay. 4-way. How many positions? 2 positions, right? 2 squares. 2 positions. How many ports or ways? 4. They're numbered, right? Remember again? Touch in the square. 1, 2, 3, 4. De-energized. Is it normally open or normally closed?
It's open 1 to 2.
Trick question, right? It doesn't. There's really no normally closed, normally open. It's a double acting for double acting cylinders. So you always have one normally open valve or one normally open cylinder and one normally closed cylinder or port. Again, this is the pilot, right? The solenoid. De-energized position is down here. If this is the pilot or internal pilot or that second valve, does anybody know what that means? External pilot. We talked about that minimum operating pressure. If this pressure here, this main pressure, is below, say, 20 psi or vacuum, you need to have that pilot pressure. And that pilot pressure needs to be above the minimum operating pressure again, 25, 30, 40 psi. Good. Again, we'll talk about, I'll take this off here. So pilot pressure, that's important, right? It's a pilot line. external pilot line. We can have the same thing down here. Solenoid on the bottom, double solenoid valve, 4-way, double solenoid. Any questions?
Why would we have a double solenoid 4-way valve? We answered that with a 3-way.
And this is what you'll typically see in 4-way valves, not 3-way valves, but yeah.
But you're going to see this, you know, it's not a detented valve, but a lot of customers will call them detent. I want a detent. Well, that means you energize one coil, the valve shifts, and you can de-energize that and it stays there. So it kind of acts like a detented valve, but it's not detented. All right, it's just the nature of the valve. Now, you know, you can do the same valve with a single solenoid, but whenever you have to leave that energized all the time. If you want to keep that valve shifted, you got to leave it energized. If you want to de-energize that thing, you de-energize the coil, and it shifts back with a spring. Make sense?
And it's really weird. You'll see it on European machines where the Europeans will keep this energized, especially as how energy conscious they are. They always leave that energized. It's crazy to me. So, 4-ways. Everybody got them? Again, you could have direct acting 4-ways, right? Not just pilot operated. 46 series. Right. We go to the indirect acting or pilot operated when we got the higher flows. That's the number one reason. We'll talk about CV here in a little bit, but flow, any MAC, typically anything above a half CV is going to be indirect acting or pilot operated. Besides the bullet valves are kind of a special case, but all right. So this one here gets a little more difficult to understand, but we'll go through it slow.
So let's start with the basics.
Yep.
How many positions?
How many positions now?
3
Three
positions.
Three positions, right? Let's see. Can you draw this? How many ways? You said 4?
5 port and 4-way.
5 port and 4-way, yeah. It's 5 ports, right? 5 ways. 1, 2, 3, 4, 5, right? You only pick one of the squares, right? You get the same thing up here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? So it's 5 ports. And what did we add? If we looked up this up here top there, what did we add? What port did we add?
5, yeah.
Number 5, yeah, an extra exhaust port. And why do we have typically an extra exhaust port? Each side of the cylinder, right? You want to control both sides of the cylinder if you're coming back through the valve. But yeah, you can control both sides.
So that leads us to that flow control out of the exhaust of the valve. Mm-hmm. So we want to meter out, right? Always meter out. Well, where do we meter out? We can meter out right at the cylinder, and that's what I prefer. That's what everybody prefers. But what if that cylinder is built into a piece of equipment that you can't get in there and adjust easily? Okay, a lot of companies, a lot of places will have a valve manifold, and on their exhaust ports, wherever it might be, they'll have a flow control in there, and it's still a meter out flow control, but it's considered a flow control exhaust. All right, so it not only has like a muffler on there, but it has a little screw that you can adjust that flow, and that'll meter out, okay? So if we just had a 4-ported valve, a 4-way valve, we could only adjust that metered out flow in both directions of the cylinder. So extend and retract are both going to be metered out through that same port, so we can only adjust that speed one time. But with an extra port like this, now we can extend differently than retract. Okay, so it's very important.
Yep. Now on a 3-position valve, the most important position is this center position, right? Anybody know how we get to that center position? So if we have if we have pilot valve here, pilot valve here. How do we get to that center position? Energize both of them? No, that's a bad thing to do in these valves. De-energize both, but how does it still go to the center? Yeah, springs. Yes, springs, right? We're missing some springs. So there's physically 2 springs inside the spool. There's some 3-position valves on the bottom there. There's 2 springs on each side. Whenever you energize one, it shifts the spool to the one side. When you de-energize, those springs center the spool internally to the valve. That make sense? So,
Are all 3 positions designed that way?
that I'm aware of, yes. All 3 positions have that same centering function. Yes, yes. Now, the nomenclature on this, what do we say this is? What type of 5-3 valve it is, right? It's a 5-3. 5-3. How do we know it's closed center? Remember, this is the most important center position, right? 1, 2, 3, 4, 5. They're all blocked off, right? So we call it CC or closed center.
Most common 3-position valve that we offer. All right.
Closed center, right? Now there's different types of 5-3 valves. That's next, but closed center. So everything, if you had that cylinder and you extended it in one direction and you de-energized it, it centered it, it extended the cylinder. When you de-energize it, all ports are blocked. What do you think is going to happen to this rod? So you extend it out and you de-energize it, it springs to the center. What's it going to do? Stop. Locks it right there, right? Now, we wouldn't do that for safety or for a long time, but that's what it would do. It would stop in that position. If we change this
Do they make 4 3s?
to
4 3s.
3 position.
Somebody does.
Everything we're gonna sell is a 5.
okay. So now, what do we call that 5-3 valve? Sorry? Open? Open center. Very good, Tasha. Very good. Yeah. Open center, right? We call it open center because the inlet is blocked, right? It's blocked off. And both cylinder ports are open to atmosphere. So at that point, if you had that in the de-energized state, you could take this rod, just move it back anywhere you wanted to, right? Because both this port and this port are open to atmosphere. So we can just move it in position. You might use it for setup, something like that, right? So that is open center.
So I want to give you an example of where I learned this before I worked for NEFF. Chris knows this one all too well, but we were automating some machine tools, some lathes, and we were putting a giant slide on the door to open and close the lathe door so we could service that thing with a robot, okay? Well, that lathe door, we had light curtains on it, so if anybody got in the way, the lathe door would stop, right? But we put the slide on top, we put a 92 series valve out there and said, I wanted that thing, if anybody breaks that light curtain, I want that valve to stop dead, stop all motion. So what valve did I pick? I chose a closed center valve. Well, that was a mistake, and I'll tell you why. Had a guy that was really, really fast, loading the lathe, and the door was starting to close. He stuck his hand in there, broke the light curtain, but he was fast enough, the door caught him, and it kind of stuck him in there. So he's crying, and it's not really hurting, but he's stuck. So he's an animal in a trap here. And what do? The cylinder wouldn't move, the slide wouldn't move either way because it's closed center. So that valve, the only way we got him out was, I thought quickly and said, I need to take one of the tubes off. So I disconnected one of the tubes and we can open the door. So we got him out. So of course we did a big safety audit after that and went back to the drawing board and decided we need an open center valve. Why? So we still stop all motion, right? So that door still grabbed his arm, but he was able to just push it out of the way, So we were able to do this thing, okay? And that's still what they have today. Now we'll talk about the next iteration of a 3-position valve, and then we'll talk about applications for that. Does that make sense to everybody though? Why you'd want an open center versus a closed center?
Huge difference.
I just wanna make it clear that I told him that.
We'll talk offline
I don't
about
believe
one.
that, but okay. Does anybody know what that is? Pressure center, right? So what do you think that double acting cylinder would do if you just de-energize it right now? If that was extended right there, what would that cylinder do?
It would depend what you had, what kind of cylinder it was. Oh, that one there?
That one there, yeah, that's the double acting cylinder right there.
The extend would.
It's already extended. It's already extended.
Oh, stay.
It would stay right there, right? You would have pressure on both sides of the cylinder, right? We didn't get into the cylinder schematics yet, but you know, we'll do. Right, so you have pressure behind the piston and pressure in front of the piston, right?
So is it really gonna stay there, Dave?
In theory, it's going to stay there. For our purposes right now, yeah, we're going to talk about that in a minute, but yeah. Would I use that for a long term? No, absolutely not. And why is that, Jeff?
Because the surfaces are different for the piston because
Surf-
of the rod.
Surface areas, that's right. That's right. We'll talk about it a little bit. Josh mentioned it before. F equals P times A. Force equals pressure times area. You have this area back here. You have this area is the same as this, right? But we need to subtract that area of the rod. So there's different areas, so the forces it's going to want to push out, right?
So if we have equal pressure on each side of that, pressure times area equals force. We have equal pressure, but our area changed, okay? So what's that do to our force? Changes our force. So we have more force pushing than we do retracting. So that cylinder, so if this thing was retracted and we de-energized that valve, it's gonna slowly creep out until it's fully extended because there's more area behind because, you know, we have the rod taking up some of our area there, okay? So we have more area, so our force has changed. We have more force extending than retracting. Does that make sense? Good question.
Yeah, you wouldn't use it on a rotted cylinder, would you?
So this is a rodless cylinder. So if we wanted to stop this thing mid-stroke or someplace, or if we just want to stop motion and we wanted to stay put, that's what we'd use that for. It's almost virtually the only application we use a pressure center for. There are a few others, but they're very uncommon. Or a dual rod, yeah. So a dual rod has a rod coming out of both ends, all right? So that area is the same on both sides of that piston.
That's
Good,
good job there, Doug. When he says dual rod, some people may not know. There's a rod coming out the back of the cylinder too, right? There's two reasons. One, you can use that. The other reason is the forces are equal on both sides, right? Force this way, force this way. And it also gives you more bearing support. So you have a bearing here and a bearing here. You still wouldn't want to use some side load, but you get some advantage on it. Cool. So this is pressure centered. So Josh.
Pressure center. So how many positions do we have? 3 position, right? Is it a normally closed, normally open? It's a pressure center.
No, it's just, if it's
Okay.
pressure centered, it's not.
So
Yeah.
if a customer says I need it normally closed, explain to them that it's a pressure center. So that 3 position, it's a 5-ported valve, so it's a 5-3 valve, all right? So if you look back at that schematic, you can start picking out those valves that are double solenoid, 3 position, pressure center, open center, or closed center, okay? So the most common is the closed center. The next would be the open center, and the least common would be that pressure center, just because we don't use them very often, because we don't, you know, it only goes on double rod or rodless cylinders typically, okay? There are other applications out there, but they're very rare.
And that I'm aware of, every 5-3 valve is pilot operated. Always going to have pilot operated on it, right? Because this is a spool internally. You have this centering, and this is a stroke. You know, the stroke might be a half an inch or whatever. The coil on each end would look something like that if you had a direct acting valve. Yeah.
Does that make
Way too
sense
much
to
power.
everybody, why the coil gets so big? Because a coil, we're just creating magnetism, right? So the further we get that spool away from its source, the least amount, or the less magnetizing force we have, the less magnet force we have. So we want to keep that stroke short and use air pressure to move that spool instead of magnetism. Does that make sense? Okay.
And for you guys that haven't been to Mac school, you'll get that beat into your brain.
Yeah.
For sure.
For sure.
Cool. Any questions, right? Position is the square. Ways, or how many places it touches one square, right? So 5, 3. Indirect acting or pilot operated, whatever you want to call it. Either way, you kind of go see it both. Solenoid, spring centered. Josh will go in and talk. There's other operators, manual operators, air pilot operators. Actually, we'll talk about that real quick. All the valves that I drew up here earlier, including this one, you can have, you still have this spring, right? You got to have the spring to center it. But you can have, I'll draw it on both sides, air operated, right? So you have this 5-3 valve way deep in the machine. You can bring a signal, a pilot signal, in to actuate that valve. So all you're doing is supplying air. Air shifts the spool, and you get this position. You de-energize it, the springs take over, it goes back to that center position. Same thing up here. You supply that signal pressure, some type of just pilot pressure into it, shifts the spool, you get this position, de-energize, this spring takes over, back to center. It's just another operator on top. And we'll talk about that, and here are some operators.
And where would we use something like that? Yeah, so if you have an explosion-proof environment, or you have like an intrinsically safe environment, something like that, and we don't want to put coils out there, we can put.
Run an air line. No pneumatics out, or no electrical signal. It's all a pneumatic signal. That's all it is.
And that does come up. I mean, we see that. We see that in pulse valves. We see that in regular, 4-way, 3-position valves.
We use those out at the airport for our flight crash simulator.
Okay.
Liquid propane.
Okay.
Oh yeah, for sure. Yeah, you want to. It's definitely explosion-proof area. Yeah.
Yep. Yeah. So, any questions about this? So
This is on the test. I promise you. Ask questions.
Yeah.
There's the one question is.
Can you show the open center, just the middle
Yeah.
square?
Make sense? Yep. Cylinder ports are connected to the exhaust ports. Yep. In the de-energized middle state.
any other questions? Good.
What's the 5-port and 4-way look like? Because you're not going to have 5 ports on the schematic.
You won't have it on the schematic. You'll have it. It'll look like the 4-way. It'll just be
It's going to have one exhaust.
one exhaust. Exactly. It's like this.
So you might
You just really don't know from the schematic.
You don't know. That's all internal to the valve. Yeah, exactly. You don't know from the schematic. Yeah. You would determine that where you would be put your. You could still use this one, the four position 2-way. I'm sorry, the two position 4-way. You can have this. You would just use your flow controls directly on the cylinder itself. That's all. That's how you get that separation of the exhaust ports. You wouldn't want to restrict it at the valve. That's all.
Make sense?
Yeah, it's maybe off topic, but it's always fried my head. To do like vertical rod lock applications, what would a schematic look like for a vertical rod lock?
There's better ways to do vertical rod lock. We'll talk about that. We talk about those pilot operated check valves. It's definitely the best way to do it, but we'll show that. But yeah, that's a good question.
Yep.
Yeah,
You got a
can't have
question?
that's a more mechanical. The rod lock is actual mechanical, but yeah, we'll do it pneumatically.
Close center, the concept in center position is to lock position, right? Same thing with pressure center. Is this gonna hold position?
Well, it depends on what you're working on. If you're working on a rodless cylinder like this, where your areas are the same on both sides of that piston, then it will technically lock that in place, okay?
But one good thing about that is because that you always have air on it, so you always have positive force. So if leakage is the key, and that's what we'll talk about with Matt's position about the rod lock. the leakage. None of that's not zero leakage. The MAC valves aren't zero leakage, so you're gonna have the leakage. That's when you use that closed center, it locks it in, but you have to compensate for that leakage. Yeah, that's
Exactly what we did.
exactly. Yeah, it's not a good idea. Yeah, yeah. It works for about 5 minutes, and then things start to drift.
Yep.
But yeah,
Yep.
yeah. But we'll talk about that, how you get around that.
Okay.
The rod lock situation is bad because it would bleed, and then when you try to cycle it, then you had nothing to.
Exactly.
close off.
Yeah, yeah. That's where the pilot operated checks come in. Those are way, way better.
All right, so let's talk about some common valve components. So we know that ISO schematic, we know how these valves work now. We know what we're doing, you know, if we're looking at a schematic, we know what they're trying to accomplish. But now let's talk about common valve parts. So these are your common valve parts. I recommend taking note of those. The body, the coil, the armature, pole piece, poppet or spool, return spring, solenoid operator. And there are more parts, but these are the most basic and common parts.
Hint. Right?
Yeah. So this is a direct operated valve. This is a cutaway of that. This is your poppet. Okay. Notice that it's a poppet and not a spool. So this poppet works between this area here. It never slides past that area. So a poppet has a positive seal, comes up and compresses the rubber a little bit. A spool actually slides through a bore, back and forth, in and out of a bore. Okay. So this here is a spool. So this guy here is going to slide past that opening. This guy actually protrudes into that opening a little bit and only moves that little bit. Okay. But that is the difference between a spool and a poppet. Those are common valve parts. Your solenoid. Your solenoid's on the top of your valve. You can see that big black thing there on the top. Your operator, you have a manual operator here in the top of most of your MAC valves. You can get extended operators, things like that as well. Your pole piece, it's hard to see, but your pole piece is down in here, and it's actually what's pushing and pulling on your poppet. What else? Your armature, that's your actual armature there of your coil. So those are your basic parts of a valve. This is actually a 92 series valve that's pilot operated. But notice that this pilot portion over here, is that a direct operated or pilot operated valve? It's a direct operated valve, right? So all we're doing is taking this direct operated valve and putting it on the side of this to operate our main valve, okay? Because we need more flow. We need more stroke out of that spool to get more flow out of our valve, okay?
And a rule of thumb, when we go from this valve, this style valve, the direct acting, to the indirect acting or pilot operated, it's about a 0.5 CV. Once you get above 0.5, MAC moves to the indirect acting. Now, bullet valves are a special animal, but typical rule of thumb.
So
We'll talk about CV in a little bit.
drawing, being that that's a direct.
That's
operated-
indirect.
Yep.
This is direct acting. This is direct acting, but the whole valve is indirect acting.
Yep,
right?
I get you.
Yep.
But going back to the schematic side of that would be where you showed that dotted line has externally piloted.
No, it doesn't have to be externally piloted. It's just that portion right there. This portion, this little pilot symbol,
Yep.
is this entire valve. Now this solenoid is this solenoid, right? But this is just the pilot operated doesn't tell if it's direct acting or indirect acting, but it's 99% of the time direct acting on most valves.
If it's indirect acting, if it's pilot operated, now we've got a valve
On a valve.
on a valve on a valve.
Yeah, yeah.
Which there are applications where we do
Yeah.
that, but they're not common here. Okay. So common valve components, I think we're clear on that. Valve activation. So pneumatic valves are activated in a variety of ways, manually, solenoid operated, or air piloted. So that's what we were talking about. That pilot operated, we're going to use an air source to activate or deactivate the valve. Solenoid operated, we're going to use electrical power, creating magnetism. And then a manual valve, I got a manual, yeah. So this is a manual valve. Instead of having a solenoid or a pilot operated valve here, this is a manual valve. It has a lever, it could be a push button, roller ball, something like that. I'll pass that around, but that's just a manual valve. Now this one is detented, okay? So whenever they say detented, it stays where you put it. all right, but it is a manual valve. They have these that are spring loaded, so they're momentary, so you push it, and as soon as you let go, it springs back out, or vice versa, all right, but this is a detented version. So pass that around, you can take a look at that. Manually activated valves are typically switched open or closed by a foot pedal, toggle, actuator, handle, knob, or push button. There's a lot of different actuators out there that they use to activate and deactivate valves. Solenoid operated valves are use an electrical coil. They're typically 24 volt or 120 volt AC. And then anything in transportation, almost anything in transportation is 12 volt except locomotive or 24 volt AC.
72 volt DC.
72 volt DC. It's a weird thing. But you're going to see...
You're thinking of the car washes.
Car washes, yeah.
Car
they're
washes.
12 volt AC.
It's weird. If you guys ever come across a car wash, just pay close attention. It'll say 24 volts, but it's 24 volts AC. I don't know why the car wash industry standardized on it, but just so you know. The new stuff, now if they're designing, it's 24 volt DC, but for forever, for the last couple of years, it's been 24 volt AC, so just keep an eye on that stuff.
Yeah. So 99% of what you're going to see out there are 24 volt DC. You're going to see some 120 AC stuff out there, and then anything in transportation is going to be 24 volt DC, by and large anyway. Piloted valves, are operated by an external air source, such as a solenoid valve or something like that. So these could be, if you look at we don't do a lot of this. I still get into this every now and again. I love doing it because it's like a riddle. But if you look at air logic and try to figure out how to do something with just air pressure, you're getting into using pneumatic timers and things like that. There's no electrical at all available. You have to do it all pneumatically and go from this valve to that valve to that valve to that cylinder to that gripper to to do that. You can do it all pneumatically, all right, and without using any solenoid valves at all. But it's rudimentary, it's old, and it's finicky. So everything we use now, almost everything we use now are solenoid valves. We use electrical sources to shift everything, unless it's explosion proof or something like that. So these are what you're going to see, like Dave mentioned earlier. Yeah. You're going to see, some of them are going to say cylinder, they're going to be stamped CYL, or A or B if it's a 4 or 5 way valve, or number 2, number 4, number 5. Exhaust, it might just be exhaust, it might be exhaust A, exhaust B. It might be R or number 3. And then your inlet is usually it says in or number 1, but you do see P for pressure every now and again too. But that's why, Dave and I both love ISO, because it's a standard. We're all talking the same language, whether we're talking to Europeans or we're talking to Americans or we're talking to Germans. It doesn't matter. We're all talking the same stuff, and makes things a lot easier and cleaner. Still don't like the metric system, but all right. ERT and DRT. Anybody know what that stuff is? What it means? This is very, very, very important. Some applications it doesn't matter at all, but this is very, very important. This is a big, big point to make between MAC and other valves out there. But there are other valves out there that are just as fast, but there's other problems with them. Energized response time means from the time we energize the valve electrically to the time the valve actually starts to shift, starts to flow. Okay, so that time, it might be 5 milliseconds, it might be 20 milliseconds, depending on the valve and the type of valve and the type of pilot. De-energized response time is the time it takes from the time we turn the power off to the time that the valve starts to close the flow off.
The key there is starts.
Starts,
right? Some manufacturers will do, once it gets to full pressure, that's a function of flow. That's completely different. It's a function of that doesn't matter for anything. We're talking about the solenoid, how far, when you energize it to where it starts to flow. It's very key.
Is everybody clear on that? So this is actually some screenshots of the TLD5 and the traces that we do. If some of you guys have done TLD, maybe even some of the old TLD3s or whatever, it's a traveling lab demo, and we use that to test the speed of our valves, the repeatability of our valves, and we usually use that in comparison to a competitor's valve. Not always though. I use it quite a bit in high-speed testing. If we need to meet a certain speed, we need to test that and prove that to the customer. And you better have your ducks in a row, because I've gotten to the customer and they have a oscilloscope hooked up and I'm using some electronic oscilloscope and our numbers didn't match and never won that business. Okay, so the ERT and DRT are very, very important. But these are some just screenshots. So this line here is when we energize the coil, and then from that time to the time it started to flow here, that would be our ERT, which was 9 milliseconds in this screenshot. DRT, same thing. This was several traces. DRT is this time to where it started to stop that flow, to turn the flow off. And the DRT was 2.6 milliseconds. Why wouldn't it be the same? It might be on some valves, or very close anyway.
The solenoid is powered one direction, spring the other.
Exactly.
Spring, yeah.
Yeah.
Spring's always constant force, right?
Yeah.
So it's right there. As soon as you de-energize, it's moving. There's no delay or lag.
So if you need to hit a certain speed, I had a customer that said, hey, I need to extend a 3/4 inch or a 20 millimeter bore cylinder 1 inch and get it fully extended and fully retracted in 28 milliseconds, 26 milliseconds, something like that. And I said, well, we have fast acting valves and we can go, like, my ERT is like 5 milliseconds, and they're going, yeah, but we have to get things moving. Well, that's a function of flow. So like Dave said, we need to hook that cylinder up with some switches and actually make full cycles and play with some overlapping and things like that to be able to meet high speed. And we use the TLD to do that. But really what it comes down to is ERT and DRT. If I'm trying to meet a certain speed, and I did meet the speed that they needed, okay, and they thought I was a hero, the key was, can I do it repeatedly? Can I do it every single cycle? Because we barely got there. I mean, we're splitting hairs. We barely got there, but can I do it every time? And we could. So that's why we won the business and the competitor lost. They could do it too. They proved that they could do it, but they couldn't do it repeatedly. They couldn't do it every single time. And that's what matters. So ERT and DRT are very important, but also remember that repeatability of ERT and DRT are very important. We're not going to cover too much of this because Dave covered most of this in his schematics there, but we do have valve ports or ways. So I want to make a point to, I want everyone to know that a position and a way, or a port and a way, are the same thing. Okay, so you're going to see some customers say, I need a 5-port valve. Well, that's a 4-way valve or a 5-ported 4-way valve. They're going to say, I need a 2-way, 2-port, 2-position valve. And you're going to be going, is it a 2-way? I don't know. Well, ports and ways are usually used interchangeably. We like to use ways, and I think that's the standard, but you're going to see that out there. So 2-way, 3-way, 4-way, and then a 5-ported 4-way. We've covered all that. Single solenoid, 2-position, double solenoid, 2-position. Again, we covered that stuff. 3-position closed center, 3-position open center, and then a 3-position pressure center. That's what we're talking about. There's not, everything Dave drew seemed like it took a while, and we had to figure out, what's this, what's that, what does this all stuff all mean? At the end of the day, these are our valve position options, and these are our port options. So you can deduct, by looking at a schematic on the side of a valve, you can deduct whether it's a 2-position or a 3-position instantly, and then you count the ways, and you can say, all right, that's a 5-ported 4-way or a 4-way valve or a 2-way valve. You can deduct all that stuff very, very quickly. What that schematic won't tell you is how much flow you can get through that valve, how big that valve is, what the port size are, things like that. Yep, I think that's it for that one. Port nomenclature we covered. So minimum operating pressure. I want to hit this one more time just to make sure everybody understands what minimum operating pressure is. MOP, M-O-P. Does everybody understand that? Minimum operating pressure is the minimum pressure we need to the valve for the valve to be able to shift. If we cannot meet the minimum operating pressure in our inlet port, we need to externally pilot the valve with pressure that's above the minimum operating pressure.
What would I have to do to this ISO symbol to make it externally piloted? What would I have to add? Dash line, right? To the pilot valve. External pilot line, right? And that's, you know, greater than the minimum operating pressure. It depends on the valve. This one, 3-position valves are the higher mop because of the dual springs. I think they're what, 30 psi?
35.
They're 35 psi. So just reference.
Yep.
Okay, so I guess I'm gonna say going back to the question that I asked before about externally piloted or externally, that's externally piloted, we're saying, right?
Yep, externally piloted.
Into a pilot solenoid.
Yep, it would be the same. So you would have to have it above the minimum operating pressure
Okay.
for spring. Yep.
Now you need to do that because the mop of the main.
The main spool, exactly. Yeah, and it'll say right on the valve too, like the 92 series. It'll say exactly what that minimum operating pressure is.
We can pass this around, but if you look down here, it says 20 to 120 psi. So our mop is 20 psi. Now, that's what that valve needs to be able to shift using the pilot air from the inlet. But if we needed to supply externally piloted pressure to that, then we can go back to 120. So we can run negative pressure through it. Okay.
Gotcha.
So the big 59 series valves, we use those a lot in vacuum because we need a lot of flow, big ports, and those we have to externally pilot every one of those. They're a pilot operated valve, they're not direct operated because they're giant, and we have to externally pilot those because we don't meet that minimum pressure. Not all valves have a MOP. Which valves do not have an MOP? Direct operated, yeah. I think we covered the rest of that. Real world examples of that, we'll cover that here in a little bit. Valve symbols, Dave covered all this. So the green and the blue are your two different positions. So that'd be a 2-position valve. Your left actuator or your actuator is this would be a manual valve with a spring return. Everybody get that? And then how many ports or ways do we have on that valve? So if you take the blue box alone at 1, 2, 3, 4, 5 ports. Okay.
Colored, I can't even see the color. Oh, maybe it's on the side.
All right. So this valve over here, this would be a 3-way valve. 1, 2, 3. 2-position. What's this? Solenoid. And a spring, direct operated. Yep. Okay. So this is all the stuff that we covered. 2-position, 2-way, 2-ported. So notice it says 2-way, 2-ported. It's another way they're going to confuse you guys. So when you see this, customers send this to you. When you see this stuff, don't let it confuse you. A 2-port and a 2-way, they're the same thing. Ports and ways are the same. Okay? So 2-position, 2-way, 2-position, 3-way, 2-position, 4-way. You can add 4-ported if you'd like. 2-position, 4-way, and so on and so forth. These are some of the actuator symbols. That's not an exhaustive list. There are many, many other actuators out there, and I think people are still producing more today. But the most common, you're going to see your manual actuators or manual. It's just some kind of manual button there. A push button, a lever, a foot-operated mechanical detent. The solenoid is your most common, obviously, for us. Internal pilot, external pilot, that little dotted line like Dave showed you, and then so on and so forth.
One thing I want to point out is you don't have to have 2 solenoids on these valves, right? You could have a manual operator here and a solenoid operator here. You'll actually see this a lot in transportation. Like you have to actually, the truck driver wants to get out and actually manually move something. You can actually do that as well. Versa valves, they do a lot of that stuff.
Mack trailer.
Mack trailer does some things.
They have the 800 series. They have a solenoid on the top, and then they actually have that external source as well to do that from the cab.
I'm going to use a pilot solenoid with a manual override.
Pilot solenoid with a manual override.
Yeah.
I mean, you could do that. It would be a custom thing.
Well, it's just one of the symbols, that's why I asked,
Yeah.
Which one?
Oh.
Oh, that's
that
all
one.
of them. That's just these
Yeah.
these all have. I never really show it. These all have manual overrides, like Josh showed. There's, I mean, you can put a manual override here if you want, but that's kind of a given thing. All of the Mac valves have manual overrides, all of them. Man. So it's
Yeah.
So the 3-position valves are 4-way valves, not 5-port, or not 5-way.
That's where you get
you have
confused.
4-position, 5. Yeah, they're
The 5 ports, like when we were.
4-port or 5-way. Yeah,
Yeah.
it's just a nomenclature, like the way they call it. Yeah.
Yep.
There's typically
So-
5 ports.
Now, they just
Two
call
true
4-way
5 ports.
Yeah,
They're
but they're
two
4-way,
exhaust
right? They're not-
4-way valve.
So
yeah.
they're
Yes.
5-ported 4-way valves. So the 4-way means that you have an inlet pressure, you have exhaust, you just have 2 of them, but you have exhaust and you have cylinder port A and cylinder port B. So there's 4 ways, but it's a 5-ported because we separate each cylinder to its own exhaust. So we're just adding 1 exhaust. That's where it gets confusing. So I'm glad you're asking the questions because
No, I
that's where
understood.
customers.
Earlier, we said it was 5 ways, and that's why I was confused. It's actually a 4-way valve.
It is a 4-way
It's called
valve.
5-ported 4-way. 4-way, yeah.
So whenever I'm telling you ways and ports are the same, that's probably where
that
that
is that
confusion's
one.
coming
Yeah.
from. Just because, you know, a
only one valve.
5-ported, it has 5 ports, but it's still a 4-way valve.
Well, I see what Matt's saying, because you got 5-3, so it's up there, versus.
No, I mean, I understand, that was more of the question, but you actually have 5-way on one of your slides earlier, but there's not actually a 5-way valve.
No.
No, but it's considered 5-ported 4-way. Yeah. All right, other pneumatic symbols. We'll burn through this real quick. Air motors, we don't have a lot of those. We don't deal with a lot of those, but you're going to see air motors. Don't get those confused with air compressor. That's this guy here. So the compressor, don't think that, the beginning of their schematic has a big air motor or something. That's usually a compressor. Check valves, spring-loaded check valves, cylinder with a spring return. That's this guy here. So spring returns, and we'll show you more about that. Double rod, double acting, like Dave drew, the double rod there. And then we've got, your cylinder, your double acting. Filters, coalescing filters, lubricators, all that kind of stuff. These are just some common symbols out there. You don't need to memorize all these things. They're just, and there's many, many more. These are just some of the most common ones. Okay.
Yeah. So,
All right, so let's look at a few applications here, and then we'll take another break. So 2-way valve application. Does anybody know what this application, our number 1 2-way valve application that we run into in the field? Pulse valves. So it's a 2-way valve, so we don't have an exhaust. Air comes in, it blows out to atmosphere. That's what that means, out to atmosphere. There's nothing to exhaust. So if you're using a blowgun in the shop and you're blowing off the workbench, you don't need to exhaust that air because you're blowing it to atmosphere, right? That's a 2-way valve. 3-way valve application, spring return cylinder. I have that one actually hooked up here. So you see your 2-position 3-way valve down here at the bottom. We know that, right?
normally closed.
Normally closed. We got our arrow here, our springs here. This tells us that we're closed. 3-way, 1, 2, 3, and it's a 2-position, 2 boxes. Okay. And then the cylinder up top, that's a spring return cylinder. So that's this guy here. This is a common application. So we have a lot of customers that use 3-way valves on cylinders, but they have to be a spring return cylinder because there's no way, we only have that 1 cylinder port. So we can tell it to either retract or extend, but how do we get it to do the opposite? Okay, there's a couple different ways we can do that. We use a spring return like this guy here. So if we extend this guy and then retract him, it's exhausting here. But if I kill the pressure here, it's a spring inside there, a physical spring. Okay? So why would we use a spring return cylinder? Does anybody know?
If you want that thing to retract, if you ever lose power.
Exactly. We want that thing to retract whether we lose power, whether it's a fail-safe, we don't want that thing hanging down there as the conveyor's coming. You know, we had some kind of failure or something like that. The valve failed, the airline blew, something like that. It's going to snap that cylinder off. So we want that thing to spring return. Okay. We'll get into this a little more deeply later, but these two cylinders are actually the same stroke and the same bore, but this is a spring return cylinder and this is a double acting cylinder. So why is it twice as long? We got to have a giant spring in there that has a certain compression rate. And so what's a weakness of a spring return cylinder or a spring extended cylinder? The spring. It's a failure point. Those springs break all the time. You can hear that thing in there. It's brand new. But that's a lot of crunching and compression in there, okay? There's not much you can do about it if you own a spring return cylinder. Double acting saves you space, but you got to have two cylinder ports on your valve. So you got to go to a four-way valve. That's just kind of how you still can do it with a single solenoid four-way valve. So you don't need to have two solenoids. You don't have to have two outputs, but it saves you a lot of space there, and it gives you a little more control. Does anybody know why this extra port's out here? If it's just a spring return, all I need is pressure to this side. Does anybody know what this port's out here for? So we got to have some kind of relief out here. Whenever I extend this thing, that air that's trapped in here has to go someplace, so it has to go out of that vent. We'll talk about that a little more later too when we talk about cylinders. But why does this one have a fitting in it? Why is it threaded? Not a pressure center, but we can add pressure to that and retract it. Okay, so if our spring did break or something like that, we can still get that thing back. So a lot of companies, they'll request it's a spring return cylinder, but they have a threaded port out there on their vent. That way they can still give that thing air pressure just like a double acting cylinder. But if they lose air pressure or something like that, they still have that spring fail safe that's going to spring return that thing. Okay. All right, so very simple application. That's what I have hooked up here. It's energize it, extends, de-energize it, retracts. Okay. Four-way valve application. That would be this guy here, and we can hook him up real quick. So I have him hooked up to my three-way valve here. So three-way valve, double acting cylinder, works great. What happened? Valve's working great. Cylinder worked great, but how do I get it back? Yeah, we need an extra cylinder port. We need an extra airline to get it back. So a three-way valve is not what we're going to use. So if you look at the schematic there, we have a four-way valve operating a double acting cylinder. So what we can do, and we can hook this guy up here. Incoming pressure. Okay. So now I have a single solenoid four-way valve, like what's drawn there. Oops, I didn't have it hook the other one up, sorry. So now we hit the button, it extends. When I retract, or when I let off the button, it de-energizes the valve. The valve spring returns back to its original position. Okay, make sense? All right. So then we move on to, this is a three-position open center. So we can hook this one up as well. So you can look at this and tell right off that it's a 3 position, right? It's got 3 boxes. And we can tell it's an open center because of that center position. All right, so we have that open center. So I extended, but what's happening? Goes back to the middle, which has pressure on both cylinders, both cylinder ports. So each one of these have pressure on them. So
No pressure. It's open. It's open center.
open center. I'm sorry, open center. Yeah. My bad. So open center. So now I can move this thing back and forth. What's happening to the air on the back side of that piston? It's exhausting back through the valve. That's our open center. All right. If I go the other direction, same thing, but it's still open center. So if I've got my little Philippine guy that got caught in his door, he can get out. All right. We didn't trap him this time. All right. And I thought I had a closed center in there. Yeah. So we'll hook this one up real quick here because I want to show you the difference. The guy that got trapped in the door, by the way, he's fine, just retired this year. And
no animals were hurt during testing?
He's got both arms, everything's fine.
What?
Thank God, right, Chris? All right, so this is a blocked center. So, maybe. Well. So this is a blocked center or a closed center. So I extended it, retract it, extend, retract, everything's fine, easy. But what if I get halfway here and I have this block center now? I can move it a little bit because air is compressible, right? But I got him trapped. I got his arm good. He's not getting out, okay? So that's what that blocked or closed center does. That's all it is. And if I'm fast enough there, you can stop it wherever and block that center. Now, would we use this as a safety feature? No. Why? It's going to extend over time. Well, this won't extend over time, but it'll creep. So if there's any weight or anything, any weight bearing on this at all, it's going, if this was in a vertical application, it's going to creep down, all right? Because you've got leak by in the cylinder, you've got leak by on your valve, nothing is airtight, okay? And air is compressible. So it's not a good way to do any kind of safety, anything. Don't ever think that, well, I can give them a block center and that's an extra safety feature. It is not, okay? All right. And then, so this one, I'll just explain on the screen. This is a 2-speed D-cell circuit. So, knowing what we know about schematics now, right? This one is going to allow you, all right, this is our main valve. This is 2-position or 3-position? 2-position, how many ways? Or ports, 5-ported 4-way. All right, because we got the 2 cylinder ports and we've got 3 ports on the bottom. Each are, has its own exhaust. Now, this is a very simple application. We're going to extend or retract the cylinder. But what we're doing in the middle here is kind of interesting. So right now, if we extend this cylinder, we give this thing the extend, it's going to say, all right, it's going to flow up and it's going to extend. Does everybody see that? Flowing straight through the valve, right? But what happens if we de-energize this, it's going to be closed, all right? So now this thing's it's going to be closed off, but we shifted our valve here and we want to go back. We want to retract. Well, now what happens? We're closed off here. So this flow path is closed. Mm-hmm. So what happens? It has another path here. So what happens? What is this? It's a flow control. So it's a D-cell circuit. So we wanted to extend at full speed, but we want to retract at a slower speed. Okay, so that's all that is.
Do you have to also add that valve in, or could it just be the flow control?
Yeah.
So this one is a 2-speed D-cell circuit. If it was just a D-cell circuit, then we wouldn't need that valve. But it's a 2-speed. So we want to be able to say retract at high speed or retract at a reduced speed.
Or even halfway through, right? You can retract like full speed halfway, and then shut the valve off, then it slows it down. So.
Yeah. So if we want to get out of the way a little bit, and then we don't want it slamming back, we can activate that extra valve. So there's all kinds of things we can do, but knowing the schematics, what's going on here with the schematics, it makes it a lot easier to understand. All right. This one's going to be a little bit hard to understand for the lower experienced people, I guess. But this is that pilot-operated check valves we were talking about earlier. This is it's important to understand this. If we use this more in pneumatics, we're going to help more customers. We're going to build more robust systems and sell more valves, period. So we've got a 4-way valve. It's a 5-ported 4-way valve. It's a how many position? 3 positions. So we've got springs on both sides, solenoids on both sides. We've got an open center. And then we have 2 pilot-operated check valves, and we're calling this a work holding circuit. Would we use this in a safety environment? We could, but we're not going to certify it and say, well, this is a safety circuit. But this would be a way of adding some additional safety. So what happens here is if we energize this side, we're going to send air this direction. It's going to flow past. It's going to open that ball check up, and we're going to retract, right? No big deal. So we're holding pressure down on the piston. Everybody got that? This side here, if we want to extend that cylinder, we're going to shift this valve the other direction. Now we're going to send pressure to this guy. It's going to come up through here and push this ball off, and it's going to extend, right? But what happens here? It's blocked. It's pushing that ball against the seat, so it's blocked. Okay, so this is a pilot-operated check valve. But notice this extra little line here. This is an extra little tube, and this is your pilot source. So whenever we energize this side to extend that cylinder, it's blowing back past this guy. There's no pressure over here. There's no pressure down here. This is all exhausted. But we're also giving pressure to this pilot. So this valve is going to shift over and open this up. So now we can flow out and back through our valve. Make sense? But what happens at that point? This guy is checked. We've added pressure here. He extended. That pressure can't get back by that ball until we shift this thing back, give this pilot source, this pilot valve, pilot operated check valve, a pilot source. It's going to shift over and free flow back through the valve. Does that make sense? So there are thousands of real world applications for this exact circuit or something very similar to this out there. One that saved my bacon in the past, spline roller application in my previous life. Tailstock was coming forward. It used to be hydraulic. We had the machines rebuilt, went to pneumatic. We had a giant cylinder bringing a tailstock in, pinching parts between center, and then we'd roll these giant spline racks over top of that part and put a spline on the part. Those cylinders were massive. When we supplied air to those cylinders, it would steal a little bit of pressure from that tailstock cylinder, and our tailstock would just kind of back up just a hair. You could barely see it move. But now our part wasn't held between two centers solid, so now it could wobble a little bit. So we were having all kinds of problems with our gears, our splines. All right. So the way we solved that was I put one pilot-operated check valve on that cylinder. So on one side, on the extend. So whenever we extend that cylinder, it comes in, pinches that part between centers. That is locked. That is pilot-operated. That pilot-operated check valve checks that pressure until I give that cylinder a retract signal and uncheck that pilot valve. That thing's going to stay checked. They're still running like that today.
The big thing about that is, right, we talked, these valves are not zero leak, right? There's actually quite a large leak through some of the MAC valves. You can get these at 0 leak. That's the key.
Does it matter how close you put your check valve to your end of cooling or whatever it is?
Always closer the better.
Closer the better, yeah.
Flow controls, every external accessory valve, the closer to the actual application, the better. Always.
The reason is air is compressible.
It's less volume, right?
Less volume of air, less compressible that air is, you know. So this is, everybody understand how this works? So we're just, instead of using a solenoid, now we could put a solenoid valve in here, that would work too. But this is a pilot operated check valve that is, it's a very simple device. You know, it's going to get some pilot source whenever we go ahead and try to extend that thing. It's going to give this thing a pilot source so this thing can retract. Or exhaust, I should say. All right, electrical connector options. Again, if you want to start a fight, talk to some of your old school guys about electrical connectors and which ones are better. Sometimes those are interesting arguments. We understand valve function, actuation, porting, symbols. How do we connect the power source and get things moving? All right. Flying leads are literally leads coming right out of your coil. They're just flying leads. You can get them at different lengths. The most standard are 18-inch leads coming off of the valves. You can get those at 96 inches. There's customers that order them with 96-inch leads. Doesn't make a lot of sense, but why do customers use flying leads instead of a connector of some sort? Cost. That's all it is. Conduit connectors, and we'll talk about those here. You can connect flexible conduit or hard pipe conduit right to your solenoid valve there, so conduit connectors. We use those a lot. Some of the older hydraulic equipment, things like that, they want to protect all those connectors and all the wiring and everything else, so they put them in hard conduit.
Explosion-proof valves too.
And explosion, yeah.
You have to have conduit connection.
Have to have them, yeah. DIN connectors, the most common connector in the world for valves. Quickly being displaced by M8 or M12 connectors, and then plug-in connections, which we can discuss later. We'll talk about these things individually now, but do you guys know what DIN stands for? That. You don't need to know that, don't write it down, unless you're really that big of a nerd. But that's what it stands for, but what that means in German is the German Institute for Standardization. So why do we have different DIN connectors out there, and why do we have different connectors for valves out there in general? Does anybody know? A little history. So it started out with DIN connectors. They came up with this standard because everybody was doing something a little different. So they standardized on a DIN connector, and it was a big A-type, industrial type connector, big DIN connector. Well, valves kept getting smaller and smaller, and we're getting more flow out of a smaller package. So then they downsized and downsized, and those are our DIN connectors. Well, now valves have gotten so small, we got bullet valves that are tiny, tiny, and we're using Pico connectors. We're using, what's the other connectors they use in bullet valve? JST. So we're using all kinds of different connection types because we're getting smaller and smaller and smaller, okay? But it's important to understand the difference between these different DIN connectors. So voltage and wattage, does everybody understand the difference of voltage and wattage? If you don't walk away with anything else from this slide, it's that wattage is very important to flow. So if you want to make a valve operate faster, you need a higher watt valve, higher watt coil. Okay, so write that one down. The most common voltages, like I said earlier, are the 24 volt, 120, or the 12 volt DC, in mainly transportation. We've got some Amish that use 12 volt DC for things too. So we do stock a little bit of 12 volt stuff outside of the transportation realm, but most of it's 24 volt. There are tons and tons of voltages and wattages out there. Mac, they wind their own coils, so you can get just about anything, any coil wound that you want or need or dream of. But we try to stick to what's most common just because we stock it. Numerous wattages available as well. Wattage is overlooked, but it's important to consider when selecting a valve. I had an application this week that popped up, and they wanted a 1/2 watt valve, and Mac discontinued those valves. They'll make them custom but they're a finicky valve because a half a watt valve doesn't have a ton of shifting force. And if we don't have a ton of shifting force, we can't have a higher spring return force. So the valve is just a weaker valve. So what becomes most important if we have a weak shifting valve? What was it? No. Weak shifting valve, you better have some very good filtration, very clean, dry air. Okay? Because any particulate gets in there, and I'll show you at lunchtime here, I'll show you a little example I do. But any particulate that gets in there, any moisture, anything like that is going to end up causing problems with your valve shifting.
Yeah, if your customer asks for anything under 2 watts, come ask Josh and I first.
Yeah.
Don't just sell it under 2 watt coil.
Yeah. Our standard
typically
is
not a good idea.
standard is 5.4 watt for us. We do sell a lot of them at the 2.4, 2.9, some of them at 1.8. But if, like Dave said, if you get down to a 1.8, we need to have a discussion and make sure that customer knows, what they're doing, and we know what they're doing. Otherwise, you can sell whatever you want, but then you're responsible. You have a customer that's angry at you. Like I said earlier, wattage can affect response time greatly. If you want a faster valve, you need a higher watt coil. A lot of the bullet valves, what are they using? 12 watt coils in some of those bullet valves?
You can make them up to 150 watt coils.
Yeah. It's massive, but if you need to move fast and speed is the key, we need to go with a higher watt coil. Does anybody know the downfall of using higher wattage on your coils? Heat. So there are mods out there for long energization, but if you're using a crazy high watt coil, some of these really fast applications, we use what we call PWM, pulse width modulation, where we're turning the valve on, getting the valve to shift, and then after that we flutter the valve on and off for a few milliseconds just to make sure we're holding the valve open or closed, whatever it might be, and we're not letting the valve shift back. But that greatly reduces the heat. Everybody understand? All right, so we'll talk about flying leads and all these connection types. We're going to burn through this pretty quick because there's not a lot of content here. BA on the Mac valves denotes flying leads. See how the leads are coming straight out of the coil? Mac, they're not the only ones with flying leads. Many other valve manufacturers have the same thing. Flying leads are usually your most cost-effective option. Conduit connectors, a couple different types, but they're made to connect your conduit straight to your solenoid there, so there's no exposed wires. The CA has flying leads coming out of that, but it does have a conduit connector, so you can come out of there, connect your conduit, run your flying leads through there, and make a connection that way.
And you can see on the explosion-proof coils over here during lunch, you can see the explosion-proof coils has the conduit stuff here.
Explosion-proof, that's a requirement. They have to have everything closed up right there. So explosion-proof, you're always going to have that conduit connection on them, and it's big and bulky, but that's what we need to keep the risk of spark down. AA has a little
wiring box
on there. It is a conduit connection, but you do have terminals in there that you can actually wire to. It's, if you got to use conduit connector, that's my favorite, just because you don't have the flying leads out there. DIN connectors. So what you're going to see, I'll beat Dave to it. The standard B, it's usually a BI. You're going to see a BI for industrial. So I pulled this off the Max site, but it says industrial standard B, but understand that most of them are going to say BI. It's very, very, very important that you make sure it's the industrial, not just the B, all right? Because there's a different spacing, and you see the 11 millimeter spacing between the pins there. The regular standard B is 11.
10.
Oh, was it 10? Okay. And same thing with A, industrial type A, 18 millimeter, and then this littler guy here. This is the standard C, but again, CI industrial. Okay. And if you get on the MER site and you're trying to find a cable for your valve, it's easy to pick the wrong. Make sure it's industrial. It's easy to pick the wrong DIN connector. Now, the industrial standards are the standards, and they're the most common by and far. So, you're not going to see many other standards out there that aren't the industrial. They are the most common type of valve electrical connector. still today, which is pretty odd, especially with the M8 and M12. M8, they call that the Pico. You'll see that in Mac terminology a lot. M12 connectors, they're used. That's just because valves have gotten smaller and smaller and smaller, and it's an easy connection, and it's been proven over the years it's a pretty solid connector. Becoming more and more common. If you have a customer that needs an M12 connector and they need a valve fast, Murr, and I think there's another manufacturer out there that has them, but I know Murr has the DIN connector that it's just a basic DIN connector and has M12 or M8 that comes off of that.
I was gonna say Canfield has them. Canfield has them, yeah.
Yeah. So Canfield. Yeah, that was the other one I was thinking about. So these are becoming more and more common.
M8, M12 are definitely the most robust, best IP rating. Problem is they cost effective. They're not very cost effective.
So Pico is M8 and M12?
It's M8. No, just M8.
M8.
Just Mac calls it M8. Yeah.
Yeah. Plug-in valves. Does everybody understand what a plug-in valve is? This is for new people. Whenever you're looking through the online Mac documentation, or I don't know, even some of the older catalogs. You had a NEFF, I think. Even some of those, they say a non-plug-in valve, and there's some. You can get very confused. A plug-in valve means that it plugs into the base. All right, has nothing to do with your electrical connector necessarily. Okay, so the valve is going to plug into the base. Your electrical connector is in the base, so it does have a little bit to do with the electrical connector, but there's nothing. A lot of people think the plug-in valve is a DIN connector that plugs into the valve itself. That's not what they're talking about. The valve plugs into the base. Okay, so there are terminals in here, and this one's actually left off of here, and you can see there's little terminals here. That's for your plug-in. That's where your valve electrical connector is made. And then this is the Myo 67 unit, so we're communicating through circuit boards in the base. I don't know if we have any Mac Connect in here, but in each base of the valve, there's a small circuit board in there that plug into one another, and whenever you bolt those together, that's what makes your electrical connection. Your valve plugs into that, and that's how we're communicating either over a field bus platform or a 25-pin D-sub connector or something like that. Okay, so everybody clear on that? Plug-in means the valve plugs into the base. All right. Examples on a trainer board, we've kind of done that, but you guys feel free at lunchtime or even after the training or whatever, come up and you guys can play with this board. We can talk about how all these things work. Ask questions that you're too embarrassed to ask now. Fun fact, if we have a valve in stock with a different connection type, we can usually swap the coil with something else. So if we have this 92 series valve that has a DIN connector coil on it, a lot of times we can swap the components in the valve and put a plug-in coil on that and make that a plug-in valve, or vice versa. So especially during the COVID excuse, we had tons and tons of customers coming to me saying, I need valves so bad, I'll take anything. Well, we were pulling stock from warehouse 2, we were pulling stock from other NEFF warehouses, but we did a lot of converting valves from this connector to that, or this voltage to that voltage, or whatever else. So we can usually make that work. So if you get a quote back from inside and they say it's going to be 8 to 12 weeks, and that's a problem with your customer, don't even send it to the customer. Send it to Value Add, get a hold of Dave and I, whatever you might want to do, and we'll see if we can build it from stock and get you something going faster. Does that make sense? When you do come up here and look at this, there are 2 little connectors in this base here. That depends on what base you get. This guy here is a single solenoid valve, so you only need a single solenoid base on there. These are double solenoids, so you need both of those little connectors on there. That's a double solenoid base. So what I normally do, if I have a single solenoid valve and I have double solenoid valves, I just give them all double solenoid bases. Where can that get me in trouble? Anybody know? We run out of contacts. So you can use up to 32 solenoids on the Myo 67, but
Solenoids, not valves.
solenoids, not valves. So that's 16 double solenoided valves. But if I have 5, or let's say I have half of them, 8 of them are single solenoid and half of them are double solenoid, and I use all double solenoid bases, that's it, I'm out. But if I have one extra valve, I don't have enough outputs to fire that valve. So you're going to want to change that to single solenoid for those first 8, and then double solenoids from there.
And if you also you do that, it also in the programming. Solenoid 1 is 1. Solenoid 2 is actually solenoid 3. So you got to skip multiple ones.
Yeah.
So just be careful.
So, what's that?
Stop doing that.
Yeah. So it does make it easier, and we stock more of the double solenoid. The reason we stock more of a double solenoid base is because you can always remove that extra set of terminals in there and change that. But we don't do enough of it anyway. And then we got Mac Connect. So Field Bus is great. IO Link, the new Myo Link manifolds are great. But if you've got a guy that doesn't need any of that stuff, doesn't need that connectivity, that Field Bus connectivity, we can just use the Mac Connect with the D-sub connector. We can do a 25 pin, a 9 pin, a 15 pin, whatever it might be. And we can also do some customs with this too and add some different types of connectors in there. I've seen some big military connectors and stuff we've done on those. But Mac Connect looks very much the same as these bases. They just have that circuit board that plug into one another. They are a little different, but really it's if you can kind of see, there's a little circuit board in each one of these and some pins, and they just kind of plug into each other. And then there's a strut that goes through and ties them all together. Okay, that's Mac Connect. Then we talk about Field Bus. That's our Myo 67. You see this, I think this is an Aventix or SM's, that's Aventix. But that's their Field Bus option. Product agnostic, see? Field Bus benefits, you can help, it can help with diagnostics in a few ways. In a number of ways, I wouldn't say a few ways. Such as through the web server or status inputs to the PLC. No longer needed to connect each individual valve wire to the PLC, so that's nice. That D-sub connector, you still have to land the other end of that someplace. This is all plug and play. And you can do a lot of other things with the Field Bus manifolds, like adding digital I/O boards and things like that. We can do analogs, a couple different analog cards. We have a Power Plus module. You can add up to 12 modules on this thing. It can get massive. But you can do a lot of work from this and pull some of that I/O out of your cabinet and put it at the point of use. And this is, these are wash down. Most of them out there now are wash down rated. But remember, if it's wash down rated, you need wash down mods on your valves, and you need to cover, put plugs in each of the ports that you're not using. Okay. Any questions on Field Bus? During the COVID thing, we sold a handful of these with just comms modules and no valves because they couldn't get I/O cards. So there was a few customers that got desperate enough that bought the comms module and a few I/O cards and put their I/O out at the point of use. Just something to think about. All right, so we're going to talk about actuators. Does everybody know what an actuator is? Definition's on there if you want to read it. Actuator is something that creates mechanical motion. So you have customers calling actuators grippers and valves, cylinders, rotaries, all that kind of stuff. They call them actuators. Okay, so an actuator creates mechanical motion. It's really what it is. A pneumatic actuator uses compressed air to do that. There's electrical, mechanical actuators, things like that as well. But what we're going to talk about today are basically cylinders, rotaries, slides, grippers, and the differences and advantages. These are slides on the screen here. To give you a little head start. Cylinders and slides, what are the differences? So this is a cylinder up here. They're susceptible to side load, mainly because if you can see this guy here, I still have this. So this guy out here, side load is this. See how that deflection happens? That's going to wear that bearing seal out there. If I'm pushing down on this and retracting it and extending it with a load on it, it's not going to last very long, okay? So what that's going to do is wear out these bearing surfaces up here, and what that's going to do at that point, you're going to get some slop in there, but it's going to leak. So you're not going to be, the cylinder's just not going to last very long. So if we have side load and we need an actuator, we usually go to a slide. So they have this big bearing block here. I will say, pay very close attention to these different parts of a cylinder in a slide. Take note of those. Toolbar, that's this bar out here that you mount your tooling to. Bearing block, you've got guide shafts that run through your bearing blocks, and then your air cylinder. All right.
It's usually called a tooling plate, by the way. I've noticed.
Tooling plate,
tooling
yeah.
bar in.
So there are many different types of slides out there. There are 4-post slides. There are square slides. There are basic slides like this. Lots of different slides. But the difference between a cylinder and a slide are just a cylinder doesn't have any external support. A slide does. That's the main difference. Okay. Everybody good here? Everybody got their notes?
Remember that.
Yeah, so these different components, these are the basic and common components. We can go into more detail, but these are the main things. One other thing before we move on here, this band right here, this is your magnetic band. So you can get cylinders with or without magnets. So if you know you're going to need positional switches, you make sure that whenever you're sizing your cylinder or selecting your cylinder, that you're adding that magnet to it for whatever switch you need to use. All right. If you don't know, ask the customer. And if you still don't know, unless they're giving you a hard no, I'm not going to use switches, add the magnet to it. It's a couple bucks, and now you know that you can add switches later on. All right. Or transducer, or whatever you might need. Okay? Everybody good on that? Single acting versus double acting. So I think we kind of covered this, but we'll go over it again. This is a single acting. It's got that spring inside, so its spring retracts or extends. And there are some disadvantages. They're longer. They're more heavy because they have that heavy spring in there, and that mechanical spring component that can break and change over time. Advantages: it has that default position, so if you need to make sure that thing's out of the way, that helps get there. It can be controlled with a simple 3-way valve, so you only need that one cylinder port we talked about. So this little guy up here can operate that in both directions. It's extended, and all we're going to do is exhaust that pressure that we added, but the spring's going to take over and retract it. Does that make sense? Okay. Double acting cylinders are way more common. Not that single acting are not common, they're just not as common. Double acting cylinders, you're going to give air pressure one way or another. It's going to extend or retract. So double acting cylinders can be single rod like I show on the screen here. It can be double rod. It can be the rodless slides. But that double acting means that it has 2 ports, and we're going to give pressure to one port and it's going to go one direction. Give pressure to the other port, it's going to go the other. Okay, no spring involved. Advantages: they're a lot more compact. Obviously, this guy's a lot shorter than this long guy here. Better control over speed. Anybody know why there's better control over speed with a double acting versus a single? Yeah, so the spring is inconsistent. We'll just say that. Number one. Number two, the spring is only so fast. You can only do so much with the spring. The double acting, there's all kinds of things we can do to get extra speed out of that cylinder. One of the high-speed applications that I've worked on, I was talking about earlier, we had to use 2 3-way valves. Instead of using one 4-way valve to tell it to go one way or the other, I used a 3-way valve and a 3-way valve. And what that did was it allowed me to overlap those signals. So when we have energized response time, I know what that is every single time, and I know it's consistent. At least with the Mac, they're very consistent. So if I have 9 milliseconds every single time of energized response time, that's 9 milliseconds that I can't do anything else during that time. I'm limited. So the only thing I can do is try to eliminate some of that time, which is how would I do that with my valve? I call Mac up and say, hey, I'm at 9 milliseconds. I want to go faster. What are they going to do? What are they going to say? Up the wattage. All right? Remember that. Wink, wink. Remember that. Higher wattage, right? But if I have 9 watts or 9 milliseconds of energized response time, I can't change that without changing the valve. So what am I going to do? Well, I want to try to do other things while that's happening, right? Same thing with de-energized response time. I want to do other things while that's happening to soak up some of that time. So I can send the signal to extend, and right before I get to full extend, I can shut this signal off, de-energize it, and this guy I can fire ahead of time. What's that do? It does 2 things. It gets pressure in my tube, right? It gets pressure primed up and ready. And it also, if I time it just right, I can use that air pressure as a cushion. So I don't come up and just slam. I'm going to come up and just kiss it and bounce off and go back. And I can do that in both directions. So now, the energized response time is going to take me 9 milliseconds here. So I got to wait until I hit my switch, energize it. Now I got to wait 9 milliseconds. I don't have 9 milliseconds, right? With 2 3-ways, I can energize this guy, maybe 12 milliseconds before this guy hits full stroke, and I know 9 milliseconds, I'm going to start to flow, and by 12 milliseconds, I'm going to be full pressure and starting to head back, all right?
And here's something PhD did with bullet valves, 2 3-way bullet valves. They put it for like cylinder ports, so you can pass that around, but that's exactly the applications Josh talking about.
So those are just 3-way valves, those 2 3-way valves, but they're bullet valves, direct operated, and that's what we can do with that. We can overlap those signals to speed that process up and soak up some of that. Now, there's only so much we can do. The cylinder's only going to go so fast, but that dead time, that de-energized and energized response time, that's time that's wasted. It's like my drive time. I'm going to drive two and a half hours home tonight, and while I'm driving, what else am I going to do? Well, hopefully, I'm not sending emails and things like that, but I'm going to try to get something else done. I'm going to try to multitask, right? That's time that is, unfortunately, it's just time I have to waste. I have to waste, so I'm going to try to do something else and productive in that time.
You can shop for my Christmas present.
I could, yeah. We're going Christmas present shopping, aren't we?
Oh, yeah.
Yeah. Anyway,
So do you always want to run a cylinder full length? So just as I'm thinking here about your time waste, let's just say you only wanted to use a 2-inch portion of that sweet spot, or I'm going to call it a sweet spot. Could you preload both sides and not use the full stroke?
well, you wouldn't do that with air pressure necessarily. You would do that with a mechanical stop.
Yeah. I would get a smaller cylinder. You get a cylinder for 2-inch stroke, yeah. You want to go from, cylinders are made to go from point A to point B. Nothing really in between, yeah.
The biggest issue with that is, you have all that volume that you have to fill. So you could overlap that signal. Now you've got 2 3-way valves, and now you've got control. The controls for that have to be pretty doggone fast and consistent. The valve's very consistent, but your controls have to be that consistent and fast as well. That time that it takes to send that signal has to be consistent and it has to be fast, and there's a lot of extra cost that goes into that. So no, get a shorter cylinder. You don't have that extra volume anyway, but it can be done. Disadvantages: the cost. They're not that much more expensive. More complex plumbing, just because you have to plumb an extra tube up there. It's not that complex, and you must use a 4-way valve unless you go with the 2 3-way valves, which is even more complex. Everybody clear on that? Does everybody understand how this works? So we give it pressure here, fill this volume with air, sends the piston back. We give it air here, fills that volume and sends it forward. But notice the volume in here is much different than the volume in here because of that different area. We got that rod in there. So that's why whenever we give it that pressure center valve we talked about, that it's going to creep out over time. Okay. Multi-stage and power cylinders. Anybody ever sold one of these? Anybody ever worked with one of these? Jeff has. Good, yeah. So these are probably underutilized. Maybe So power cylinders give you extra power because you've got basically 3 cylinders force all in one. So you can multiply your force by, say, 3 or 5 or 10 times, depending on how many stages you have. But the reason we use these in industry is if we don't have a lot of space side to side, center line to center line, to put a bigger bore cylinder out there to get the force we need, we can use a power cylinder and get the force that way. We're going to extend the length. Now, when we extend that length and we add all these extra stages, the stroke is what we sacrifice. Okay, so that's a pretty long cylinder there. And if this was all piston, we would have a lot of stroke, but we don't. We just have a little bit of stroke. Okay, so power cylinders, you're going to sacrifice stroke for pressure, for force, and then, but you're also going to, the advantage is you can get closer center to center. So you're going to extend the cylinder length, but you're not going to extend your stroke just to get center to center. Okay?
Get a lot of force out of shop air with one of these things.
A lot.
Like close to hydraulic pressures.
Yeah. So different types of slides. We have the rodless slide. I'll pass this guy around. He's heavy, so don't drop him. But he moves. This is an amazing slide. That's a rodless PhD slide. Those guys are pretty bulletproof. And I think it's the next slide. I'll show you that band on top. So when you're passing this around, this stainless band on top, I'll show you how that works. It's like this magic that everyone thinks that's going on there. It's really nothing. So we have our rodless slide, and then we have our rodded slide. So this guy runs on bearings, bearing rails. This guy has guide rods and bearing sleeves, and with that bearing block there. So each one of them, they handle side load. They handle load differently than just a cylinder would. Okay. Any questions there?
Everybody knows what cantilever means. It's fixed in one point and it extends out past it, right? So that's very important.
Yeah. So that cantilever thing is huge, and we've got some different slides that we can offer that, we can get. We can go long distances with a lot of support, but we add length, and it can be a hazard, bumping your head on it, things like that. So the rodless actuator. So this is that band. This is a cutaway of that band. So that band runs along here, and it just runs up and above the shuttle here. Okay. This is your piston. Some people call it shuttle. There are magnets in here, so you can get your extend and retract and positional feedback. But that stainless band in there is just running up and through there. So there's no black magic there. Customers don't really understand that either. The biggest thing, the only reason that's there is to keep debris out of that slide. So the better band that they put in there and the better magnetic seal they have on that, the longer that cylinder will last. So if you look at rodless cylinders and you look through the catalogs, if you've got a competitor out there and you're looking through their catalog, look at the life, the expected life, linear inches of travel in the life of that slide, and you'll see a big difference in quality. It'll tell you what kind of quality that cylinder is or that slide is, just by but 80% of that is that band keeping debris out of it.
And there's two types of these slide, the rodless style. This is the saddle is attached to the piston. It's physically attached to it by bolts. They also have a magnetically coupled rodless cylinder. There's some limitations to them. Speed is one, right? If you're moving too fast, that piston, it can uncouple from the slide. It's not very heavy on forces, but there's another version. We do not sell them.
What's an advantage of the magnetic coupling?
Cheaper, cost effective. Yeah. Less leakage.
Yeah, and if you hit something, it breaks through.
Yeah, it doesn't break, snap. Yeah.
But they're you can't go very fast with them typically, and the speed thing is what really kills them. I think. Any questions on the rodless? So if we wanted to stop that rodless cylinder or rodless slide somewhere in its stroke and hold it there, what valve would we use? 3-position, close. Pressure center, yep. That pressure center would put pressure on both sides. Area is the same on both sides, so it kind of locks that thing in place. All right. All right, rod lock. So we talked about rod lock a little bit earlier. A rod lock is actually a mechanical device. It'll hold pressure. You keep pressure on this and it keeps it unlocked. And basically there's two collars that grip that the shaft of the cylinder, and they're offset. Whenever you have air pressure on them, they're lined up and allows that rod to slide between there. But as soon as air is lost, they kind of offset and lock that thing mechanically. So would I stick my head under a guillotine with a rod lock on it? No. Guys, there is no, you know, you can't treat this like it's a safety device. A lot of companies, a lot of manufacturers use it as a safety device, but there's got to be, you know, there's different levels of safety, obviously, and this isn't one that you'd put a human life or limb at risk for.
One big thing is any oil on the rod, right? Slippage. Now your forces change. It's
Yeah, so
definitely not a safety device.
And you know those rods are, you know, they're usually coated and ground and polished. I mean, they're very, very smooth. But again, these do create quite a bit of force, and I mean, yeah, I've never been able to move a rod, but it's, you know, it's a great device. I think, you know, we should use them more, but that's what they are. And you can use these on cylinders, slides, grippers, and all kinds of other pneumatic stuff. Rod locks they just stop motion, you know, and mechanically lock that motion. There are better options out there, especially if you're using grippers or any device with any kind of gearing or something like that. We can engage a gear lock on those. It's not technically a rod lock, but they still consider them rod locks for some reason. But that can stop motion as well.
Josh, it's not technically to be used for a brake, though. The stop motion.
No.
Stop motion, yeah, not a brake. No.
Right.
Hold it in position.
Lock it, not necessarily stop it.
Right. Yeah. So if you're extending your cylinder and somebody breaks the light curtain, you're not going to use a rod lock typically to grab that rod as that cylinder's moving. You want that cylinder to be stopped, and then you apply a rod lock.
Same on a servo motor, right? Yeah. You don't want to stop motion with it. It's probably a bad idea.
Yeah. So now there are emergencies where we use rod locks as an extra safety device to grab that thing as it is moving, but that's a one-time use, and then you replace the cylinder, rod lock, and everything. So that's kind of a pain. Size in a cylinder. This is a point of contention always, but I gave you a real easy example here. The customer, this is real world stuff. This was actually an application that whenever I was writing this came up. They needed 1,000 pounds of force, they needed 12 inches of stroke, and they have 100 PSI at their plant. All right, so I need to size a cylinder for that. So PhD has great sizing software on their website. Why don't they have sizing software for cylinders? Anybody know? They have it for slides, they have it for grippers, they have it for rotaries. Thank God they have it for rotaries. But they don't have it for cylinders. Why not? You don't need it. It's pretty straightforward. I mean, you know, X amount of pressure, you figure out how much area you have. You know, it's just pressure times area equals force. If they could probably create something out there for you, but all it's going to do is give you pressure times area equals force. So they don't need to create a program for us to do that. This is on the NEFF intraweb, internet, whatever it is. It's available to everybody. If you don't have it, email me, I'll send it to you. Email any pneumatic guy, they all have this. And you don't really need this necessarily. You can Google this. This is real easy information to find. But I know I need 1,000 pounds of force. I know I need 12 inches of stroke, and I got 100 PSI to work with. So how much force can I get out of a 4-inch cylinder? Well, start plugging numbers in, right? It's pretty simple. So bore diameter, 4-inch cylinder stroke, I need 12 inches. Rod diameter, we're not going to know that right off because we don't know exactly what cylinder we're going to go with, but I used a 5/8 rod or whatever there. Stroke time, this only has to do with your valves. This is going to tell you what size valve you're going to need as well. But if you ask the customer, hey, how fast do I need to go? Maybe he says it's a half a second. Maybe he says, doesn't matter, as long as it gets there before the next cycle. Might be a minute, you don't know, okay? But I use 1.5 seconds for this one. Inlet pressure is 100 PSI. If you want to size something with a little bit of safety factor built in, lower that pressure. I think Andy Bogle uses 60 PSI.
60, yeah.
Something like that. So I don't know what Tim uses, but
All the PhD stuff is set for, like I said, 87 psi, but yeah, drop it down to 75, 70, something.
yeah. So it adds a little safety factor there. You don't want to go, well, I'm going to add a lot of safety factor. I'm going to go 20 psi. I mean, your cylinder is going to be huge, you know. So just keep it within reason, but between 60 and 80 psi is usually how I size things. This one I put 100 psi in it because that's what we had here. And then the pressure drop, this is that point of contention. I use 5 psi pressure drop. This will change your valve flow required dramatically. All right, but if you know what the pressure drop is or can get a closer guess, that's fine. I use 5 as a standard and build in some safety factor, and I've never had an issue that way. If you
For all you CA guys, he uses 10, just so you know.
Yeah, CA uses 10, and he's right, always. Why does PhD not include cylinders in their online sizing software? We covered that. Just kidding, CA, if you're watching this. Notice the extend and retract forces. This is the big deal here. Extend and retract are different, so 1194 and 1165. It's not a huge difference, but why are they different? Because of that rod. That rod takes up some of that area, all right? So pressure times area equals force. That area is extremely important. The pressure is not going to change. We're going to have the same pressure on each side, but that area will, okay? So this will get it done. This will get me 1,100 and almost 1,200 PSI, and great, that's all I need. So now I can go out on the whatever site and say, I need a 4-inch bore cylinder, 12 inches of stroke, and I start adding all the goodies on there. And then I can look at the rod diameter after I pick the cylinder and say, oh, it's actually only a 1/2 inch rod diameter or whatever it might be. Plug it in here and get some better numbers. But at the bottom here, it gives you some flow. So it gives you flow in SCFM and a 1.14 CV of flow for your valve. All right, now I can go out to the Mac site and say, what valve flows 1.14 CV or more? That's a fine way to do it, but we all know that hopefully that 92 series is 1.2 CV. So that's a little more than I need there. And I do have, I could build some extra safety in there, but a 92 series valve is probably going to do this. Maybe I jump up to a 93. But now I know what valve to look at, I know what cylinder to look at, and now I just have to add goodies like switches and mounting and rod end and mount, rod and cap end mounting options, things like that, which we're going to talk about. Okay. Any questions here?
How do you calculate area?
How do you use the calculator? No, you just there's calculations. I can't remember the formula off the top of my head, but
Pi r squared.
pi r squared. Yeah.
You're on set, most of the time you're on set.
It's easier if you use diameter squared times 0.7854. That's what I use. A lot of people don't know what the radius is, but I use diameter. Diameter squared as well.
All right.
But pi r squared is definitely the. Some people don't know what pi is. Diameter squared times 0.754 is the one I use common. It's just easier for me to remember.
So cylinder accessories, like I talked about, now we know what cylinder we're going to pick. We also know what valve, just because it spit that out. So now we need to pick some accessories for our cylinder. So rod eye, rod clevis, alignment couplers, clevis bracket, eye brackets. There are numerous different types of mounting accessories for cylinders. Now, you notice most of these look pretty standard, and that's because these are all NFPA mounts. And we're going to talk about what NFPA stands for here right now. So NFPA is a National Fluid Power Association. And the ISO is an international organization for standardization.
The same organization that we did with the ISO symbols, same one for the cylinders
That's
as
ISO.
well. ISO symbol.
Okay, so the NFPA, they've got a set of standards, and usually it has to do with mounting. NFPA cylinders are hydraulic or pneumatic actuators that are modular, pre-designed, and interchangeable. So anybody see any problems with that? There's a lot of benefits there. Sounds good to me. Because if a customer calls me and says, hey, I'm having a problem with X cylinder, I can say, okay, well, what do you have? Well, if it's an NFPA, I have a drop-in replacement for it, and I can sell it to them. Where's the disadvantage there?
So is everyone else.
So is everyone
So does
else.
everyone else. So if they have a problem with my cylinder and they can't get a hold of Matt McClellan because he's out making so many sales calls he can't even take a phone call, they can cross you to somebody else.
What's that?
So there's advantages and disadvantages. Okay. ISO, same thing. ISO sets standards. This is the mounting sizes and the numbering and the schematics and everything else. That's kind of their standards. So ISO and NFPA, you're going to see a lot in pneumatics. They're both good and bad. Help me out quite a bit. Help us win a lot of business. But I don't know. We probably lose a little bit that way as well. Grippers. Does anybody know? I don't know why that is on there. Does anybody know the difference between a gripper and a clamp? Without fighting each other. Mechanical lock. So a clamp has a lock. You can remove the pneumatic pressure and it stays locked. It stays clamped. Okay. A gripper is a pneumatic device that grips, and if you lose pressure, it lets go. Okay. So that's, if you ask guys at PhD about that, there's some of the old school guys they'll fight the younger guys on that. It's a point of contention again. But if you just think about it like that, a clamp clamps and locks. A gripper just grips and lets go.
Yeah. Clamp, if you take the air off, it stays in that position. You can't, you
Stays
need
locked.
air to move it back. And we have customers that do that on mobile carts. They want to clamp something, they move it down, they can move the cart away, take the air away, move it around, it's still locked in. So.
Yeah. So, grippers, there's a bunch of different grippers out there. The two big differentiators there are angular or parallel. Does anybody know the difference, angular and parallel? This is an angular. They open up at an angle. And parallel, I don't think I have a parallel one there. Parallel, just straight in and out. They open and close that way. Okay. Advantages and disadvantages. Anybody see any advantages for angular?
Why would you use angular over parallel? Nah, you can encapsulate both.
You can
Just on the
encapsulate both.
tooling. On the tooling. Get out of the way, right? Yeah, if you're over a belt, your fingers can come completely out of the way 180 degrees, right? Parallel is just, you actually have another axis to move it up out of the way. So.
Yeah. So a lot of times it saves you an axis, saves you some controls, saves you a cylinder slide, whatever. Parallel, you can get quite a bit more force out of parallel, and they're a little more robust depending on the gripper you choose, but most of them are a little more robust. And then you've got this weird guy over here in the upper right-hand corner there. This is flexion, and anybody sold any flexion?
Yeah.
Doug, the only one I think.
And all of them.
But it mimics the human hand, so it uses tendons and has knuckles, and it bends, and you have to encapsulate parts to pick. It doesn't really have any pick force to speak of. You have to encapsulate those parts to be able to pick anything. Okay. Just a point or a little tip. Use that to get in to start the conversations, and you get some attention with that thing because it is a cool gripper.
Yeah, we'll wait. I'll tweet till rotary's good.
Okay. So rotary actuators. Rotary actuators are the most dangerous thing to size, with all of our products. Maybe some of the electrical stuff might be a little more dangerous, but as far as pneumatics go, this guy will burn you quicker than anybody else. Does anybody know the number one killer of rotaries? Kinetic energy. Speed. Thanks, Doug. Thanks for reading
Man, he
that.
can read, man.
Um,
Get up there.
So rotaries, there's sizing software on PhD's site. There's sizing software. Everybody's got sizing software for rotaries. If you call me and say, hey, can you cross this rotary and give me a part number? You might even send me the spec sheet. It might have every detail of that rotary. You send it to me. There's 100%. No, 100% I will not cross it for you. There is no crossing of rotaries part to part. We need all the application details. So I'd rather lose the sale, and I mean that wholeheartedly. I'd rather lose the sale than to give them a rotary that fails. And I've been burnt. I've burnt myself, I should say, making some assumptions, and a lot of times I'll even size everything up, and I'm very confident. I'll even send it to PhD and have them bless it again, because rotaries, there's just one little thing is off, and the rotary it just won't do its job, or it won't last. So they can be really tricky to size. We need all the application details. If we don't have all those details, like I said, I'd rather lose the sale. It's not worth creating a bad relationship, a bad experience with the customer, hurting that relationship long term. So we need numbers of positions needed. So that, it might just be 2 positions. It might be 3 or 5 or 8 positions, I don't know. Orientation of the tooling, very important. Is that rotary going to be sitting on a tabletop, just rotating this way, or is it going to be, has a load this way? Angle of rotation, how far do we need to rotate? Is it 90? Is it 180? Is it 270? Whatever it is. The load, very important again. Not just the load of what you're picking or rotating. The tooling, that tooling length and weight is critical. And then the rotation time. Number 1 killer of rotaries is, again, speed. Okay.
I want to clarify that. Speed, you can go fast. You can fucking fly with a rotary actuator. Stopping it is the problem, right? It's not the fall that kills you. Right? It's that sudden stop. That's exact same thing.
Yep. So we can go really fast. We just have to add shock absorbers, or dampeners, or something like that to stop that motion. Okay. If the rotary is responsible for handling all of that load, that stopping force, it just beats them up. Okay. Typical applications for rotaries are tables, tilting, flipping, lifting, and can you think of any others? Anybody have any unique applications that they use rotaries in? I worked on one that's flipping pancakes. That was kind of neat. But we oversized that one like crazy, because is it a heavy pancake, a light pancake, a big pancake, a small pancake? There was too many variables. But they never bought it. So
one thing I like to talk about, we talk about these rotary actuators, talk about angular grippers. Everything in pneumatics is linear force. Everything we do is linear force, and it's the biggest distinction between pneumatics and electromechanical. I like to do a little thing here. So we're talking about rotaries. I think my gears are getting worse, I don't know. So you have a piston here and a piston here. Sorry, I'm trying to get out of the way. But you have a linear force. Pneumatics pushes this rack across this way. It rotates the pinion, right? This is a shaft coming out or whatever. It rotates it. Everybody understand that? Same thing moving back. You push this side, and it goes this way. In electromechanical or robotics, whatever you guys want to call, we use a lot of motors, tons of motors. So your motor, you have rotating this way. Now it's connected to a belt or something else. So now you create a rotary motion to create linear movement. So I just like to point that out, because that's a huge difference, huge difference. So everything in robotics and electromechanical is going to be a rotary force. In pneumatics, is always going to be a linear force. Grippers, rotaries, everything. So.
Everybody understand that? Any questions on rotaries? If you have a rotary that you want to size, you need to know the minimum. This is minimum technical competency. So we need to know what rotaries are, some of the parts of a rotary, how they work, what information we need to gather to size a rotary, what kills us in rotaries, some of the advantages and disadvantages of rotaries. Those types of things that's the basics. If you get into a rotary application, please, please, if you get nothing else out of this training, get a hold of Dave or I. PhD, don't hesitate to use apps from PhD and have them help you size this thing. And you'll see even the apps guys at PhD, if you don't have one of these things that we need, one of the key pieces of information, they're just going to tell you, we need that. We're not going to size it. All right. I don't want to scare you away from rotaries, but I don't want you to get hurt. I don't want to hurt a relationship with a customer for sure. So just be extra cautious with rotaries, and I'm always happy to help. PhD's always there. I think Dave's happy to help usually.
Sometimes, yeah.
Yeah, depending on who it is, I think. But.
Yeah, as long as Ben don't call.
All right, so we'll talk about switches. Switches are not my area of expertise, but switches, we add switches to cylinders, slides, rotaries, grippers, all that kind of stuff. And just tells us whether we made it there or we made it home. Okay, so there's nothing real fancy here. There's a lot of different switches. PhD has kind of narrowed it down to the JC switch series, and it makes it a lot easier for everyone. But understand there's a ton of switches out there, and you can also use other manufacturers' switches on other cylinders, whether it's a PhD cylinder or a Bimba or an SMC. You can use switches. You can sell switches to go on to other cylinders. They're interchangeable to a point. The keys are you have to make sure you have the right magnet in that cylinder, and then you have the right mounting, profile and things. PNP versus NPN, very important to ask that question. I don't know, probably 90%, maybe 95% is PNP, and the rest of them are NPN. Place I came from, they were NPN, and it was always a pain because everybody stocks PNP but not NPN. Typical switches used in pneumatics: pressure, read, Hall effect, solid state, and prox. Solid state's my favorite just because there really aren't any moving parts there to wear out. They last longer, it seems. Common mistake when ordering switches or selecting your switches are when you select a cylinder, you want to add switches to that. Make sure that you're not just getting one switch and one cable. Make sure you're getting two of each. If they need extend and retract confirmation. If they only need one direction, then one switch and one cable are fine. Don't forget to get the targets and things like that for that switch. Some cylinders don't have the option of putting a magnet in there, so they have to work off of targets. Some of the grippers work off of prox switches, so you definitely need the targets for that. Things like that. And then always include a cable. Always include a cable. I like the quick connect switches. You can do the switches that are just pigtail switches, but the quick connect, you sell them an extra cable with that. I like that. Customers tend to like that. It's a little more cost up front, but if they have a problem with the switch, they can just disconnect that, replace the switch. Same thing with the cable, I guess. But all right, any questions on actuators, cylinders, slides, rotaries, grippers, clamps even? We didn't talk about clamps a lot, but clamps are very much like grippers. They just lock and stay locked. Any other questions? We're going to move on to vacuum.
Rotaries, there's a question here, what's the difference between rack and vane?
Rack and vane. You want to draw that?
Yeah, that's a rack. Right.
That's a rack.
Vanes, or if you're looking at a top view, it almost looks like a kind of a CRS cylinder, but this would be your rod. Your rod comes out here on the pinion. On the vane, there's a bore and kind of a stop or whatever, and you supply. Actually, it's kind of goes to the center. You supply air on this side, it rotates this way. You supply air on this side, it rotates back the other way. That's any vane.
Statement goes to shit.
Yeah, exactly. Yeah. So we don't sell vane actuators, so it's all right. So yeah, this is the main difference. It's typically these are small, very small vane. I mean, you don't get a ton of force on them, but yeah, that is the difference.
All right, any other questions? All right, my favorite, vacuum. So all day today we've been talking about pressure times area equals force. Same thing applies to vacuum. Pressure times area equals force. The issue with vacuum, everybody gets either burnt or scared or think it's some black art, is in regular pneumatics we have 0 to whatever pressure we can produce. Right? Usually it's 120 psi. Vacuum we have 0 to negative 14.7. That's all that's available. We don't have anything else available to us. So the mistakes that you can overcome by switching, changing a little pressure on the positive side of things, you run out of luck on the negative side of things. Okay, so that's where we can get in trouble really quick with vacuum. So understand that 14.7 is all the further we can get. That's perfect vacuum. Okay, The rule of thumb is every 1,000 foot in elevation, we lose about an inch of mercury. So, you know, if you're selling vacuum in the mountains, you know, you're even more handicapped. You know, you might be dealing with, you know, 10 or 12 inches of mercury, and that is it. I mean, it's, or PSI, I'm sorry.
And it's a huge deal if you have a machine builder and they're shipping stuff to Denver. It's a problem. It's a big problem. You just lost, you know, a third of your total overall scale to elevation. So.
Yeah, and so plumbing issues, you know, sizing things just on that edge, those things will all, those things turn into monsters when we ship this equipment to some places higher in elevation. You can really get burnt that way. The other thing I want to get off the plate right away is the vacuum conversion, all the different ways we measure vacuum pressure. It's 0 to negative 14.7, guys. That's what we have. But, you know, the rest of the world, they say, well, let's use KPA. And then somebody said, well, KPA is fine, but that's positive. What about negative KPA? Let's use negative KPA. It makes more sense because it's vacuum. Well, somebody came up with that. And then they got torr, millibar. They have millimeters of mercury and inches of mercury. And then they just have somebody, it was probably the same guy who came up with the metric system, said, how about just percent of vacuum? 100% vacuum is 14.7, negative 14.7. Makes a lot of sense. So does metric, but I'm American, I don't like it. So, all these things are, there's conversions out there. You can Google all this stuff and it just converts it for you. So don't let any of this stuff, if it says, hey, I'm, you know, negative 50 KPA, just Google that and convert it to whatever you know or whatever you need. We use inches of mercury almost exclusively. PIAB uses, they've been doing some stuff with torr lately.
Torr you'll see a lot in like laboratory stuff. Yeah, a lot of labs
so
use torr.
inches of mercury is usually what we're working with. So that's this inches of HG here. And it's negative 30 is perfect vacuum. You're never going to get there in industrial vacuum. You might see 28, 29 maybe in a, you know, picking glass or something like that if you pick the right cup and the right generator. But that's, they're all the same thing. They're all just different ways of measuring the same thing, okay? Don't let that confuse you. How do we create vacuum? So there's several different ways we can create vacuum. Rotary vane pumps here, these create just a ton of flow. So Julin, their motto is we can move a house with a hurricane. Well, they use blowers for just about everything. That's what this is considered a blower generator here. So this thing spins and it just pulls air in, creates just a ton of vacuum flow. Now we're not going to get real deep vacuum with this. They're just not designed that way. It's made to create a ton of flow, not deep vacuum. Okay.
And one thing with those, you can't deadhead those pumps. The blowers, you can't just block it off. You have to have continuous flow. So you have to have a diverter valve to suck in atmospheric pressure while you're not using the pumps. So they continuously run. They're made to run 24/7.
So, and we'll talk about a few of the advantages and disadvantages. This is a venturi system here. Air comes in here. You have a little nozzle here, blows straight through, but it creates this area of negative pressure there, and it tends to want to pull vacuum in there. This is not going to create deep vacuum at all. It'll create a medium amount of flow, and that's about it. This guy, you're going to see this. This is one of our competitors' designs. But you have pressure coming in this block here, comes through, and there's different nozzle sizes and lengths and different chamber sizes that create different things. One's for more flow, one's for a little less flow, one's for a lot more vacuum, a lot deeper vacuum, and you know, so on and so forth. But at the end of the day, we have a vacuum chamber here that's pulling vacuum, and that's where, you know, that's how we're creating vacuum. What PIAB uses, this is coax technology. I'll pass these around in a second. This is a 3-stage coax cartridge. So pressure comes in here. You have 1 stage, 2 stage, 3 stages. So that first stage gives you a ton of flow. That's where you get all your flow from. This next stage gives you a little deeper vacuum and some more flow. And that third stage gives you really deep vacuum and hardly any flow. So the reason we have 3 stages is because in vacuum we can either have high flow or deep vacuum. There's one or the other, and there's always a trade-off for that. Okay, so if you want a happy medium, How are we going to get there? Okay, so these are some of the ways we're going to get there. This coax technology, that's PIAB's version of meeting ourselves in the middle. Now, when I pass these generators around, you're going to see that the tips are different colors. This one's got a black tip on it. This has a blue tip on it, different sizes. So even though they've done a really good job of finding that happy medium, they've got big generators for a lot more flow. They've got smaller generators for less flow. They've got the micro generators for just a little bitty bit of flow. But they also have these different tip colors, and what those tips are for deeper vacuum or higher flow. So even though we found a nice happy medium, we still have different sizes, and then we also have different nozzles that create different things. Okay, so it's very important to understand you can't have both high flow and deep vacuum at the same time, but we can get close. Okay, this is the MIDI, the biggest guy, MIDI. This is the mini, it's the mid-size, MINI, mini. And this is the micro, because he's tiny, okay? I'll pass these around. One thing you can do, especially in this big guy, is you pull him apart, you just kind of wiggle it and pull him apart. These little windows that you see on the side here, they have to be covered up with one of these little rubber flaps, okay? So when you put it back together, it should be covering that flap up. If not, you aren't going to create much vacuum at all. There's other ways of creating vacuum, but it falls into these two categories. You either have a pump or we have a vacuum generator, okay? These are not pumps, these are vacuum generators. These are coax technology, these are venturies, okay? So a venturi, if you want to create a simple venturi, take a piece of pipe, drill a hole in the middle of it at an angle, and put air in one side of it, flowing straight out of the other side. And that angle, because that air is passing by that hole, it'll start pulling vacuum through that hole. And that's a venturi. That's what we're talking about. That's what I'm passing around here. It's just a little fancier way of doing it to get a little more efficient.
And to make it more confusing, PIAB calls them pumps.
Yeah.
I have that argument with them all the time. I just had it with them a couple weeks ago. But they do call them pumps. They are venturies, though. They're venturi generators.
Yeah. This is the newest technology. This is the SX12 or SX42. This one is broken. That's why I use it for a demo. But this is the same technology as I'm passing around there. It just doesn't have those rubber flaps. This is a two-stage. It's a little more dust tolerant. Air comes in this black nozzle here at the end and exits out the other end. But I'll pass that around too. I love these new generators. They created a lot of flow and they're very lightweight, robust. I've had like zero issues with them. So a single stage venturi, these are very common. Has anybody gone out on YouTube and looked at, what's the guy, the Dr. Vacuum, I think it is, from Vacon, the Bimba vacuum guy? So he's a great resource for basic information. Some of the things that he says out there are not correct. So just like anybody else, including myself, don't take everything for gospel, but there's a lot of good information out there. But where he goes wrong is he's focused on what he's selling, which is Vacon. And almost all of their generators are single stage generators. They create a ton of flow, but they're never going to get to that deeper vacuum level. Okay? So that's where some of the information he gives out there starts to get a little pushing it a little bit. This is a single stage, so we have one stage in the middle, it's creating vacuum, and that's it. Okay? Single stage, they're lower priced, they're more compact, there's virtually no heat because there's not a lot of turbulence there. Disadvantages, they usually have a higher noise level. Poor efficiency, they really don't create as much vacuum pressure as you need to do any amount of real work. They high vacuum or high flow, not both. You cannot do both. That's what those three stages are for. So this guy here is, you get one or the other. Multi-stage venturi, high efficiency, low energy consumption. A lot of times we're producing way more vacuum flow than we are using compressed air. So most of our generators are like that. So that three-stage really does work.
And it's almost 3 to 1. So for one FCFM, you almost get 3 to 4 SCFM in return, vacuum flow. So.
Yeah, that's a huge deal because you're wasting a lot of air. When you turn this thing on, they're loud, and we'll play with them up here, but they're loud. You're wasting some air there. High reliability. There's not a lot of moving parts there. Those rubber flaps are literally just rubber flaps. If they get clogged up with dust, usually it's because it's hygroscopic dust that collects moisture and gets stuck on those flaps, and you can just warm soapy water, put them back in service, and they run forever. The SX42, the clear one I passed around, that one has a little more dust tolerant, but the same thing with that one. If it gets clogged up for some reason, just rinse it out. Low noise level, they're pretty quiet. At the end of the day, they're all a little noisy, but they're much more quiet. And they're modularly built. This is one thing that our customers, that we don't do a good enough job telling our customers what we have and what, telling them what options we have available to them. These can be put in custom manifolds. They can, PIAB will give you the cavity drawings, and you can create whatever cavity you want and pop this venturi right down in that, in the end of your tooling, whatever it might be. So you can put these in any kind of custom application you want. We just don't do it. I don't know why. I think it might just be because we're not telling our customers that that's something that they can do. Okay. All right. So vacuum flow. Vacuum flow and vacuum pressure are different. Pressure times area equals force. So how do we get more force? We either change the area or we change the pressure. So pressure is not flow. And if you think about this, I don't want you to take this too literal, but this is Pneumatics 101 here. Flow equals speed. Okay, the more flow we have, the faster we're going to go. The less flow we have, slower we're going to go. All right? Faster evacuation times. If we have more vacuum flow, we're going to evacuate atmospheric pressure quicker. So we're going to evacuate the atmosphere that's in the tubing, the fittings, in the suction cup, whatever it might be, we're going to evacuate that faster, okay, because we have more flow. That doesn't mean we're going to create deeper vacuum, okay? Higher productivity, just because we can do work faster. Less slippage. A lot of times we can produce less slippage just because we can overcome any kind of leakage and still create, enough vacuum pick force to not move around. Ability to hold part if cups are worn. That one's a point of contention again. That one is, it's very true. If you have a cup that's just starting to crack or wear or something like that, you have enough flow to overcome that, you can keep running. Should you? No. Change your cup. That's just the way it is. But, if it gets you an extra, it gets you till the weekend, they can do PM, that's a lot of productivity.
Vacuum flow is very important in like thermoforming. And if you're trying to thermoform a bathtub, you want to get all of that application air underneath the tub out as fast as possible so you can pull it down to the mold. So that's why we use those big 59 series valves, running vacuum through them. Flow is key and stuff like that.
Flow is key.
If we go back to Mac valves, so if we just got rid of the word vacuum on a chart like that, what's the exact correlation between flow? That's measured in SCFM and then CV?
Yep, on Mac.
Yeah, so CV is coefficient of velocity. It's actually C sub V, so coefficient of velocity. So how much flow can we pass through the valve, and how much turbulence do we have in that valve that's restricting that flow? You can also measure that in SCFM. How many SCFM can we shove through that valve? It's the same thing with torr and millibar or torr and inches of mercury and all those things.
Yeah. But they're both SCFM flow.
They're all flow.
Yeah.
And on the valve side, it's always going to be a C sub V.
On the vacuum side, no, it's typically not in the vacuum. That's not the way they do it. It's just all flow is SCFM, but it's easy to take CV and transfer it to SCFM as well, so you can get that correlation.
Gotcha.
Yeah. So, flow equals speed. Remember that. It'll make things easier for us here moving forward. Now, flow can also create a lot of problems for us in the reverse, but in Pneumatics 101, flow equals speed, and that'll get you further. Does anybody know the difference between decentralized and centralized? So decentralized has one generator and one cup, or thereabouts. One generator, one cup. So this is your generator. This has one of those big MIDI cartridges in it. And that's just a housing for that cartridge. And you have a cup. So you might have, this application has 4 cups, pick in that box. Each one of those has one of these guys on it, okay? So each one of these, boom, 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 boom. Centralized means that we have one generator up top, one vacuum generator up top, and these are just cups, okay? So let's talk about some advantages and disadvantages. The decentralized, let's talk about the disadvantages first. They're higher initial cost usually. Why? You're buying 4 generators and 4 cups, and you still need plumbing and all that kind of stuff. More sensitive to dirt. Why is that? How am I going to get dirt? How am I going to filter the dirt out before it hits my generator? It's kind of hard to do, right? You can add some kind of filter in here. You could do it decentralized, put a filter in line there. It's just not very typical. So they're more susceptible to dirt. More vacuum switches needed. So in that previous application there, so this guy here, where would I add my vacuum switch? This one here? On each pump or generator. Yeah, it's a pet peeve. You would add one switch to each side. Vacuum switches aren't cheap, guys. They're in fact, my goodness, it's like buying groceries anymore. I mean, it's expensive, especially for me. So you're going to need 4 of these things to really get a good read, and then you got to do something with that data, right? The centralized, just one vacuum switch, and that generator is actually built in. One vacuum switch, and you know if you have vacuum enough to pick or not, all right? So that'll cost you quite a bit more that way. Added weight to the underarm tool. Each one of these guys weighs something, and you're adding some extra weight out there instead of just one generator. And that centralized generator, you can usually mount up on your robot arm or something like that away from your tooling, so it gets some of that weight off your payload. Advantages: instant vacuum release, smaller plumbing lines, because your compressed air line can be 1/4 inch or 3/8, whatever it might be, and then your vacuum is where you need to keep the lines large for that extra flow. Compressed air going in here can be a pretty small line, as long as it flows enough to meet what the generator needs. They're easy to troubleshoot. If this one's not picking, you're going to know it. It's just that one's not doing the job. The rest of them are. Okay. Flexibility. You can move these things around, however you need them. Increased safety. If this guy doesn't pick, but the other 3 do pick, and we did our job right, building in our safety factor, we're still going to pick the product. Okay, we're not going to drop the product on somebody or something like that. And then energy savings. Energy savings is, again, arguable, but typically it saves you some energy just because each one of these generators can be sized way down. We're not using near as much compressed air. Advantages to a centralized system: one generator to maintain. So you got one guy up there with multiple cartridges in it maybe, but it's just one generator to maintain. Lower initial cost, you're only buying that one generator. It is a little more expensive, but you're only buying one of them. Easy to add inline filtration. You can see in the picture there, it's got a vacuum filter in line. Clean plumbing, all you're doing is supplying compressed air to your generator, and then from there you're going out to each one of your cups. The way this is drawn here, I would never ever recommend that with these 90-degree fittings. That's terrible. That's the worst thing you can do in vacuum. We'll talk about that. Easy vacuum switch feedback. One vacuum switch is all you need. Disadvantages: if one of those cups fail to pick, maybe that cup got torn, maybe who knows what. One of these things didn't hit product, didn't pick. The rest of them aren't going to pick either. Okay, so when I first started, I'm thinking, well, who would ever go with this then? I still want to pick. The object is to pick the part. There are an increasing number of customers that if it's not a good solid pick, they don't want to pick at all. So they don't care. They'd rather go to centralized. They're slower acting. Anybody know why they're slower acting? Yeah, you got to evacuate all this area and your cup area. Vacuum plumbing needs to be larger, and no 90-degree fittings, or as little as, least amount as possible. The reason I don't like 90-degree fittings in vacuum, on the compressed air side, put them in there. You can put 90-degree fittings if you'd like. On the vacuum side, a 90-degree fitting is the equivalent of adding 3 feet of whatever tubing size you're using. So if I'm using 1/4 inch tubing and I only need to go this far, but I put a 90-degree fitting in there, it's like adding that much tubing. So now we don't have near as much vacuum flow because we have all that length that we have to flow through, right? Does that make sense to everybody? Mm-hmm. So 90-degree fittings are a no-no. These T's are the worst thing you can do in vacuum. And the reason being is a 90-degree fitting like the one on the end, the elbow at the end there, is terrible. It adds about 3 feet of, the equivalent of 3 feet of tubing. These T's in the middle here, the problem with that is you got to think what's happening here. We're pulling atmosphere up through here, right? But we're also pulling atmosphere through here. This point right here becomes very turbulent. At every intersection there becomes very turbulent. And any turbulence in your air with vacuum, remember, we don't have a lot of pressure. We're not dealing with higher pressures here. We can't overcome a lot of these little things. So any kind of turbulence in there costs us a ton of flow, okay? So try not to ever use T's or elbows. And if you go to a customer and they're saying, hey, I'm dropping half my product, and you go in, first thing I always look at, the first thing I always looked at is how they did their plumbing. And a lot of times, it looks beautiful. They ran that, and all the plumbing is contained within their end arm tooling. It looks awesome. But there's 19 90-degree fittings in there, and I'm going, can't do it. Or add a really big generator, one of the
And
other.
not only that, when it's in series like this, or in parallel, this one's getting all the flow. By the time it gets down here, if there's any porosities, it's a cardboard box or something, you're going to pick here, and it's just going to peel right off.
Peeling is huge. They're harder to troubleshoot too, because if one of these doesn't pick, none of them pick. So now you got to go through and try to figure out which one isn't picking and why. So again, each of them have their advantages, and they are real advantages. I like decentralized, but at the same time, the smart generators, when you're talking about something like this is 4 generators in one little manifold. Makes it really easy. And all of these, they have a lot of functions built right into them. This guy here is a dumb generator. You have to add, if you want blow off, you need a blow off check valve and an extra control valve. You need a vacuum switch, you got to add a vacuum switch to it. And then all the extra plumbing, and if you want to plumb these in series, it's just kind of a pain. This guy has everything built right in, but that's more of a centralized generator. Doesn't have to be, but typically it is. Does everybody know how a vacuum cup works? I will say this, there's been 3 people so far that have known how a vacuum cup actually works.
Evacuates air inside so that atmospheric pressure.
So you're very, very close. So we all have pressure on us right now. There's atmospheric pressure in the air in the room here, right? So that atmospheric pressure is pushing in all directions. We're not talking about gravity, so don't get confused. All right? This atmospheric pressure is holding us together. Well, it's also pushing down on the cup, up on your product. So it's pushing up on my hand, it's pushing down on the cup, so is gravity. But this way, same thing. There's pressure pushing these items together, okay? But there's also pressure inside pushing the cup up and pushing my hand down, or the plate here down, right? So all those things equal out, and they're just touching each other. So what happens when in vacuum is we're going to evacuate this pressure and turn that pressure into a negative as we can get it. But once we remove that negative pressure, we don't have that pressure inside pushing against each other, pushing in all those directions away from each other. We only have the pressure pushing those things together. So it's not only that your cup is pushing down, it's that your product is pushing up. So everything is pushing those 2 items together. All right? You're creating a black hole, basically.
One cool thing, I
Makes sense?
don't know if you guys have seen this yet, the Keynote unit, but it has a magnetic strip. The people are like, how the hell does that stay on there, right? You're thinking, you know, picks it up, it's gonna part's just gonna fall right off. The same theory as this right here. It's pulling up it's pulling up against it. Yeah, as if the magnet works. It's pulling up against it, right? Everything's pushing down against it, so it's collapsing into it. So that's a great demo of that.
Yeah, and I'll share a failure once we hook that up here. So your little failure, me and Matt had a little failure in the field, but yeah, so suction cups, foam, any of that stuff, if you remove that atmospheric pressure that's holding the parts apart, essentially, remove that. Now the part and the cup are working together to become one. They're trying to push themselves together. Now you have pick force. Suction cup shapes. There's all kinds of suction cup shapes here.
I want to think about the pick force you just mentioned. With pick force, this is still F equals P times A, right? The area of the cup.
Here, before you go there,
Good.
let's look
You got.
at this guy. Yeah, this guy.
So we'll just have a negative pressure now. That's all. It's the only difference in vacuum, right?
So where do we get our pick force from? While we're on that subject, I'm gonna skip ahead a little bit and we'll go back.
Yeah.
But where do we get our pick force from? We evacuate that air. Everything's pushing each other together. They're becoming one. Now we have some force. But if I need to pick up that table, what am I gonna do? What first thing in my little kit here? What am I gonna pick? What am I gonna look for? Maybe a foam gripper. The biggest generator I have? Biggest cup. Why? Pressure times area equals force. Okay? So this generator, this has a lot of flow, and we can add 6 or 8 of these things, these cartridges to one generator, the P6010 or whatever, and you can get a bunch of them, and create a ton of flow with compressed air. However, that little tiny micro generator I passed around, if I had to evacuate this entire room, all the atmosphere in this room, that little tiny generator will do the exact same job and take me to the exact same vacuum level as that big MIDI cartridge I passed around or whatever generator I had up there. It'll all do the same job. That tiny little generator is going to evacuate all this. It's just going to take a long time, okay? Because it doesn't flow as much as that big generator. So what's flow? Speed. So if I want to evacuate this room fast, I'm going to add a bunch of these big generators and get that flow moving. But as far as getting down to a deep vacuum, both those generators will do the same thing. So pressure times area equals force. Did I say anything about flow? I didn't. So we're not going to get any extra force out of extra flow. Okay? So don't confuse that. Don't add more flow to it or think I need a bigger generator if I want to pick a bigger, heavier object. That's not the case. It's just going to do it faster. But I need a big cup. So to pick that table, I need the biggest cup I can get, but that table we could probably pick with 4 of these cups would pick that table very easily. Okay? One 6-inch cup will pick that table very easily. One of these vacuum pad tools, and we'll hook it up and try it, would probably pick that table up itself. Okay? It's just how much area do we have. That area is what matters. So if you look at these 2 cups, a 40 millimeter versus a 75 millimeter cup, this guy has 5.5 pounds of pick force, right? So say I have to pick a 10-pound part, I'm going to have to use 3 of those to build in some safety factor to pick that part, minimum. Or I can use 1 of those and kill my safety factor, overkill my safety factor like crazy, all right? So if you can use a bigger cup, always use a bigger cup. Now we'll go back to suction cup shapes, shapes. So there's many different suction cup shapes. So that leads us to this. We have round, so we can use a round suction cup, no big deal. We have oval. Why would we use oval? Space constraints. If we need a bigger area, pressure times area equals force, we need bigger area. We need a lot larger cup. We'll use an oval cup. All right. This is going to give us a lot larger area than I can fit 2 small cups in, right? It's going to give me extra pick force. I got a pet peeve that I don't like oval cups. We'll talk about that. But oval cups are a way to get around that. Rectangle cups, we only use those in picking candy bars. They developed those specifically for picking the little Hershey candy bars, the bite-sized ones. They're really good at it, but they do have square cups, so I added them on there. All right, so Oval cups. What are weaknesses of oval cups? Orientation. So if you have to make sure these things cannot spin, they can't, if they get loosened up or get bumped, they're going to spin, they're going to move, right? So you got to have some kind of positive reinforcement there to make sure that they're not going to spin or rotate. So it's just a little extra work, but after we get by that, what else? Advantages, they give you extra pick force. There are disadvantages. Yep, this right here. So you need to come down, touch your product, and then turn vacuum on, which costs you a little time. But if you have the time, it's fine. The reason being is those edges, as soon as you turn vacuum on, those edges, you come down close to your product. These are the weakest edge because it's a long, straight edge. It's going to pull that edge in and fold it under, and now we have a leak. Now it doesn't pick anything. So a little prop for PIAB. They have one of the best designs on the market, and I nerd out on this stuff, sorry. This long straight edge, how do we make that long straight edge more rigid? They added these little wings in here, and you can see them, I'm pass this around. That little wing solidifies that edge quite a bit. So they have one of the best oval cups on the market. If you give me this cup versus 2 of the same diameter round cups and $10, I'm going to use the 2 round cups every time. I don't like them for that reason alone. Too many problems with them. Okay, but we have to use them sometimes, and it does give you a little extra pick force. If that fitting falls out of there, it's just held in there with that little O-ring. But I'll pass it around. Suction cup types. We've got flat, concave, bellows, multi-bellows, and foam. Tons of different options there. Bellows are more compliant, so if you come in, pick a product that's not straight and level, it has some compliance there. It also, whenever you pull that thing up, it comes up and has a little bit of give and a little bit of bounce. That's important in some applications. Yep. A flat is a more rigid connection. So if you have a flat cup, I don't have any handy, but a flat cup, this guy right here, when that thing grabs a flat surface, it doesn't let it wiggle or move much at all. The concave, picking domed or rounded product, we don't do a ton of that, but when you need to, it's important to have some kind of cup that'll do it. And then foam. Foam does, there's a lot of advantages and disadvantages to foam. This is actually a Jewel-In product rebranded as Kinos, if you guys didn't know that. But this is the KMG, the mini grippers. This is a foam-lipped suction cup, we'll call it. Okay. The advantages of this is you can mount these all around, tooling, different angles, different places, just like you can a suction cup. Other advantage is that foam will conform to a lot of different irregular surfaces, textured surfaces, things like that. Disadvantages are they don't produce a ton of pick force, and that foam is semi-closed cell foam, so it's not closed cell. It doesn't seal completely. There is some leakage through that foam. So you do have to compress the foam about 50% is what they tell you, and then create vacuum. Otherwise, if you come down slowly, it'll actually pull the edges of that foam in and kind of curl up. And what happens whenever we pull that foam in and create vacuum? Kills your area. So now you have no pick force. Okay, so I'll pass this around. I'm also going to pass a few of these other ones around. These are the KMGs. And again, this one has several holes in it, but it's treated like a suction cup. No generator on these. You can add a generator right to the top of them. A lot of different sizes, whatever. But these are, and then we also have suction cups that just have a foam, literally a foam lip around them. And those work well too. This one's kind of a long, skinny guy, and they have some different size and lengths. But you'll notice this hardened material in between the foam. The reason they do that is if that foam gets thick enough, it can actually fold itself over and close that hole off, kills some of that area in there. So if if you need thicker foam for a little better compliance or to conform to a certain contour of a part or something, we can still have thicker foam, but they added another layer of adhesive in the middle of it, so it adds some rigidity, so it can't really collapse on itself. So that's the only reason that's in there.
What about the ball valve, check valves that they have?
So yeah, we'll talk about that here in a second. That's a good point to bring up.
This looks like it would wear away real quick.
So all the foam, you'd be surprised, and I can pass this around too.
Looks like some of it's coming off a little bit.
Yeah, and it's been around and around. Now, the foam is a wear item. It's a consumable item. Same thing with a suction cup. It's a consumable. These suction cups, these are modular suction cups. These are the pie grips. These have replaceable cup lips. You pull that cup lip off and replace it. So this is a consumable item. However, they last a lot longer than what you think. The most demanding application that I've found so far is picking rough sawn lumber that has a lot of splinters and things. Because what happens is you pick lumber, and the next one you come up and pick has some splinters that get stuck in the material. The next one you pick, those splinters that are in there, we crush that foam, and what happens to those splinters that are inside there? They break. What's that do to the foam? It tears the center of that foam. So I've had customers that say, hey, you know, my foam isn't lasting, and I come in and the foam looks like this. It looks good. And I'm like, did you just replace that? And they said, no, it's wore out. So when you touch the foam, the center of that foam is just deteriorated and almost gone. So it's almost like it's hollow. That's because those splinters get inside there and break it apart. Okay, that's the most demanding application I've found so far. Any kind of abrasion hurts foam. That's why I always say touch your product and then turn your vacuum on, if you can, and most of the time you can. This is that easy foam that Dave was showing you there on that safe and light there. It's a refrigerator magnet. I mean, let's just call it what it is. They call it rubber steel and some other fancy stuff. It's called Easy Foam. That's the trade name for it. But it's a refrigerator magnet. Works really well. It's really popular. Customers absolutely love it because, as you pointed out, when that starts to wear out, you have to peel that off and peel the sticky backing off your new stuff and stick it on there. Well, if you don't get that perfect on there, now you got to replace it. You know? That Easy Foam, it comes with that backing on it, and you just snap it on there. The orange stuff is a natural rubber foam. It's not, we don't really use this unless we absolutely have to. It's not a great foam, but it is an option we have. But you will notice, other than the thickness, that there's a big difference in this. They call this IT foam or Italian foam, and this is the jewel-in, they call it American foam or US foam. This is much more, the cells in this are much larger than the Italian foam. And I thought, okay, all the foam is being made and cut in Hickory, North Carolina now. So we can even cut foam for other competitors' tools. The issue is here, I'm looking at this when I was in Hickory and I'm saying, that foam's all the same, guys. It's not, you know, the foam's not gonna matter. Just pick one and stick with it. And the engineers kept saying, there's a big difference between Italian foam and American foam. So when we got out on the floor, I actually tested that. I had a box with open flaps. They were not taped, glued, or anything. The box weighed 50 pounds or something like that. I hit that with Italian foam, and same thickness of foam and everything. And the box started to crown, and then eventually peeled off whenever I gave it a little shake. When I hit that with American foam, it was a solid connection, never crowned at all. And I picked that foam and I could not shake it off. So I said, what is the difference? Is it more closed cell? What is it? And it comes down to reaction. So if you squeeze that stuff, now one's thicker than the other, so it's kind of hard to tell. But if you squeeze the American foam, it's faster acting because those cells are more open. It's still a semi-closed cell foam, but the more we can snap down on that product, we grab the edges of the box, right around the top rim, it creates a much, much more solid pick. So it is there's a huge difference. Now, does that mean that American foam is better than Italian foam? Not at all. There's other applications where the Italian foam outperforms the American foam 10 to 1. That's why we have the option for both. Okay. Suction cup materials, polyurethane is the most common. Silicone's a close runner-up. Remember that. And then we've got nitrile, HNBR, foam, metal detectable, silicone, Viton, and there's a ton more. Do you guys know what the metal detectable silicone is? So we use that in food whenever we have metal detectors at the end of the line. So you've got food coming down. We have ferrous metals impregnated in that material of the suction cup. So if a piece of that suction cup, even a tiny little sliver, comes off and gets in the food, that metal detector will go off, and then they can clean the line and quarantine all that product from there. So those are huge. We're not the only ones with those at PIAB. They're all over the place. We just have a great selection of those. If you need that, you're one of 3 people that can help that customer. So make sure that we don't walk by those ones. But the most important thing is polyurethane's the most common. That's, all these blue and green cups, that's all polyurethane. This is the silicone. Silicone is very important, handles higher temperatures and things like that. Any questions on cup materials or cup shapes? Suction cup durometer. Does anybody know why suction cup durometer is a big deal? Where? That's a huge one. Sealing. So, if we have, so this guy here, this has a 60 shore durometer of 60A in the green area, and the yellow or whatever thick stuff down here in the bottom is 30 durometer A, shore A. So what that means is the higher durometer, the harder the material is. So we want a stiffer material up top on those bellows to give us a little more stability and not wear out, not crack and wear out too easily. Gives you a little durability. They call them Duraflex cups. That bottom of that is bonded together. That you can't peel them apart. They're one and the same. But they soften this bottom up a little bit, and that's just so we can seal on more product, conform to irregular surfaces and things like that. So durometer makes a huge, huge difference. If you're talking, this is a blue silicone. We won't get into this too much, but this is like a blue silicone. It's very light durometer, and that cup edge is very, very thin. But we have to have a tough material there. When we thin out a cup lip like that, it still needs to be strong, right? So that really thin cup lip does not handle abrasion at all. You put that in an application, somebody reprograms a robot, comes down, it abrades for a shift, and that cup is done. That cup lip is just gone. This is the BGX cup. That's a bag cup only. And I'll pass this one around. This is the Duraflex, and that's the dual durometer. So again, the higher durometer, harder the material. Lower the durometer, softer the material. Soft materials will conform to uneven surfaces better. But don't get that confused with thin lip. Some of the materials, we have to use a little harder durometer on some of the thinner lips, but they do conform better that way. It's just one of those things.
I'll talk about that, and I'll go run it underwater again.
Yeah. So this is the MX cup. This demo lives in either my garage or my truck. And in the wintertime, when it's like this, it gets cold. And this stuff's good down to like 50 degrees. And below that, it starts to curl up like that. And that yellow material, it's the same exact material that this is. This is just thinner. That stuff will get hard and discolored. And I don't know if I have one in here that's, yeah, this one's very hard. Actually, pass this around with that cup and feel the difference. To fix that, this is polyurethane. To fix that, if a customer comes to you and says, hey, this thing's came in like this or whatever, just have them run it under hot water, and it'll come right back. So he'll run it under hot water, and it'll be like eureka. All right, suction cup accessories. So this is something that we leave these off of the bill of materials a lot. How are we mounting that suction cup? Is it going straight on your generator? Is it, do we need some kind of level compliance there with the level compensator? There's different types of level compensators. Do we need to manifold several of these cups together? So do we need that diverter block there that your cup mounts into? These are PI-Safe sense valves. We'll talk about those in a second. These are just extensions. You wouldn't believe how many customers need extensions to get that cup down to where they need it to be. This is just a threaded mounting rod there. And then this mounting bracket here is amazing.
It wasn't even hot water. It was kind of lukewarm water.
You can just pop that on some extrusion.
Yeah, what's that?
And then
it's smidgen of water.
Mount that right to that, and now they have everything mounted and everything's good. Okay, so yeah, Dave's passing that cup around, brought it back to like brand new. So I had a customer call me and they said these cups are failing in a shift. Went out and looked at it, and it's Little Caesar's pepperoni. They're picking Little Caesar's pepperoni, and I said, "What's the temperature in there?" And he said, "Well, it's not freezing." And I said, "Well, what's the temperature in there?" And it's like, "Well, 36." And I'm like, "Oh." So we went out, I shut the line down. It'd been running for like 6 hours, and I grabbed that cup, and I mean, it was so stiff. I said, "Guys, these are the wrong cups." They said, "Well, how fast, I can't get new cups. How fast can I have new cups?" I said, "It's going to be, 2 or 3 weeks, before I can get you enough cups to switch you over." And he said, "Well, I have to run in the meantime." So they literally, for 3 weeks, took those cups. They would run them for half a shift. They'd go in, shut them down, take all the cups off, replace them, and then take them out, run them under hot water. And they did that for 3 weeks. And they had 2 sets of cups. And those cups lasted that 3 weeks. And then we got them into silicone, and they changed over silicone. Everything was good. So it is something just to remember. All right, so mounting accessory is very important. There's ball mounts there that you can change the angle of your suction cup, things like that. These guys here, these are PySave sense valves. So what this is, I don't have a good example for you, but what that is, it's a little rubber flap. You see that rubber flap sticking up over the top of it. If you have 10 cups and say 5 of them hit the product and 5 of them are hanging off, those 5 are going to get an influx of flow because they're not touching anything, right? They're just going to be sucking atmosphere. Well, that extra flow has enough, there's enough force with that flow to pull that flap over and close that valve up. So it does not close it up completely. It does leak. That's important because if we end up touching product, we want that flap to open back up. We don't want it to stay sealed, all right? So it's a flow restrictor, not a flow, it's not a check valve. It's a flow restrictor, okay?
Touch product is like the atmospheric air on the inside and down.
Yeah.
Flap that back over.
Yeah, because there's not enough flow.
Incredibly slowly.
Right, now you notice there's different colors here. And those colors are very important. Those different colors, the rubber's a little thicker, a little thinner. So depending on how much flow you have, what cup you're using, how big a cup, things like that, that flap will have a harder time closing or an easier time closing or an easier time opening. So each one of these are rated for a different amount of flow. To pick that out, to know which flow you need, which color you need, is hard. So I would recommend getting hold of Dave or myself or your PIAB rep, whoever that is, and have them help you with that. Once you do it once or twice, you can probably pick them all out yourself. And it's not hard. It's just, you'll get burnt the first time. And a lot of times what customers say is, "Listen, just get me one of each, and I'll see which one works best." Well, if you're not standing there, they probably aren't going to be happy. All right, so 2 important vacuum concepts. Again, vacuum level is force, and vacuum flow is speed or recovery. Why is it recovery? Why is recovery important? The faster I can pick apart, if a customer says, "Hey, I need to pick these things," Matt, you remember flower manufacturing? Mm-hmm. They're picking car fresheners, air fresheners for your car. They're picking those cards. Well, they have to pick those things very, very fast. Well, we can pick them extremely fast. I mean, it's in milliseconds. But we have to also get rid of them really fast. Okay? Oh, sweet. So we have to get rid of them really fast too. So picking them is one thing, getting rid of them is another. That's called recovery. So how fast can we get rid of them? Vacuum flow, vacuum pressure is not going to help you or hurt you either way there. It's all vacuum flow. So in this chart, you'll see, this isn't a great chart, but as the percent of vacuum increases, your flow actually decreases. That shows energy. Like I said, it's not a great chart there. This one we covered. This statement up here at the top is very, very, very important. I don't think it's on the test, but I'm saying it's very important to know. More is not always better. It takes 10 times more energy to generate 27 inches of mercury. It only gains you very minimal holding forces. Okay? So if you look at this, 27 inches of mercury gets me 5.5 pounds, but only 18 inches of mercury gets me 22 pounds just by changing the size of that cup. Guys, that's what we have to do. We have to understand that pressure times area equals force, we need to change that area. We don't have a lot of pressure to work with, but let's change that area.
There's only two variables, right? Either pressure or the area. Change the area. It's a lot easier, a lot more cost effective.
So really, we're not targeting on inches of mercury level. You're targeting a lift pound capacity.
Force, yeah, pick force.
Pick force.
Pick force.
But there's probably a minimum inches of mercury that you want to be over also.
There is, but it depends on the product you're picking. So if you're picking corrugate, you might only get to 11 or 12 inches of mercury. All right, but
Are you still generating the force?
how do we generate enough force? Bigger cups and a lot of flow, because we're pulling atmosphere through that.
Get it compensate
But-
for the porosity.
Yeah, but if we're picking that table, it's pretty smooth. We have a nice soft cup lip on that thing. We might hit 25 inches of mercury, and on a small cup, and it'll just go right off of there. We put a larger cup on there, and you couldn't pull it off. You know, that cup size is what changes your pick force. It's not your. It gains you very, very, very minimal in pick force by getting to a deeper vacuum. So that's why I'm saying we can argue all day about speed equal or flow equals speed versus force is pressure. We can argue all day about that. At the end of the day, it's if we break it down to the basics, flow is speed, and if you think about it like that, 99% of the time that's true. There is those couple applications, a couple scenarios where a little extra vacuum pressure does gain us a little more pick force, but it's so minimal that it's almost not even arguable. And like I said, it takes 10 times more energy to generate 27 inches of mercury, and it only gained us, it didn't gain us enough to do anything with, really.
If we needed that force on a pneumatic cylinder, crank the pressure up, right? We got 150 psi scale to work with. Here we have 15 psi scale to work with. So it's a lot easier in pneumatics to just crank the regulator up or something to get that more force out of the cylinder. It's a lot more more expensive on pneumatics to buy a new cylinder or something, right? Compared to a cup.
So a 2-to-1 safety factor in perpendicular, if you're picking straight up perpendicular to the floor. If you get into shear, we go to 4-to-1. It's very, very important. So if you're sizing cups, or if you say, hey, if you're looking at the cup specs and you need to pick 10 pounds, your product is 10 pounds, and you got a good seal and all that kind of stuff, you're going to get into shear. You're going to have a suction cup that will pick 40 pounds minimum in shear. Okay, that's just the way it is. If you go beyond that, if you go below that, you will drop product and you will be on that edge. There are applications where I've had to go below the safety factor, but I'm not going to own it. He doesn't want me owning it. I don't want to get yelled at by him. So I'm not going to size it that way and say, well, this will work or this won't work. If it doesn't have that safety factor, I'm not comfortable with it. I'll send it to PIAB and have them bless it. That's just the way it is.
And then the customer has to bless it.
Yeah, then the customer. I mean, I will not move on this at all ever again. And that's really all I have. Helpful resources. Use your boss specialist. I'm a boss specialist. Dave's a boss specialist. There's many of them in every territory. We have boss specialists everywhere. They're not all pneumatic experts, but excuse me, most of them are. Application engineer. I'm also an application engineer. You guys have them. Most of you have them out and around or available to you. Your product manager. Most of the product managers are pretty technical people. Use them. The MacValve's website, it's not great. PhD's website, not great. PIAB's website, or PhD's great. Yeah. PIAB is not great.
Horrible.
And then the in-house website, don't hesitate to use that. If you need a mod description, or if you need those calculators or any of that kind of stuff, that in-house web's got a lot of information there. It's just a little clunky to get to it, but spend some time on there. And then just use Google. If you need to convert torr to inches of mercury or whatever it might be.
CVDSFM.
What threads are compatible? Don't believe everything you read on Google. And, but Google's a great resource.